Hi, my name is Wendy Corbin, and I am reading to you the F5-201 TMOS Administration V2 study guide because when I was looking for an audio version of this study guide or any study materials, I could not find such a thing. So I'm hoping this will help some of you out there. Keep in mind when this is created. This is in June of 2019. So if it's more than a year past that date, I wouldn't recommend using this as your study guide. Overview. Welcome to the TMOS Administration Candidate Produced Study Guide. The purpose of this guide is to help you prepare for the F5-201 TMOS Administration exam. The contents of this document are based on the 201 TMOS Administration Blueprint. The majority of the information is compiled from F5 sources that are located on the Internet. This guide provides students with some of the basic foundational knowledge required to pass the exam. The resources for study also include the TMOS Administration F5 Produced Study Guide. The resource guide is a list of additional reading material that will help any student build a broad base of general knowledge that can assist in not only their exam success, but in becoming a well-rounded systems engineer. The resource guide will be available to the candidate once they are qualified for the TMOS Administration exam. Hands-on experience with the Big IP platform will reinforce many of the topics contained in the TMOS Administration exam. F5 has created a virtual lab environment that can be run on a laptop with VMware Workstation, Fusion for Mac, or in a lab with an ESXi server. The F5 vLabs can help by providing access to a lab environment in which your knowledge of the Big IP platform can grow. For access to the vLab guides and virtual machine, please contact your local F5 sales engineer. This study guide is a collection of information and therefore not a completely original work. The information was found mostly in F5 resources. All of the information locations are referenced at each topic instead of in appendix of this document. This was done to help the reader access the linked information easier without having to search through a formal appendix. This guide was prepared by an F5 employee but is not an official F5 document and is not supported by F5 networks. Section 1. Troubleshoot basic virtual server connectivity issues. Objective 1.01. Given a connectivity troubleshooting situation, consider the packet and virtual server processing order. Virtual server intro. Before we get into the study points of this section, there is some basic information you should know about virtual servers and the Big IP platform. There are some references here. A Big IP platform is a default denied device. This means that the device will not accept traffic and process it unless you have configured it to do so. A virtual server is a traffic management object on the Big IP system that is represented by an IP address and a service port, or a port number. Clients on an external network can send application traffic to a virtual server, which then directs the traffic according to your configuration instructions. The main purpose of a virtual server is often to balance traffic load across a pool of servers on an internal network. Virtual servers increase the availability of resources for processing client requests. Not only do virtual servers distribute traffic across multiple servers, they also treat varying types of traffic differently, depending on your traffic management needs. For example, a virtual server can enable compression on HTTP request data as it passes through the Big IP system, or decrypt and re-encrypt SSL connections and verify SSL certificates. For each traffic type, such as TCP, UDP, HTTP, SSL, SIP, and FTP, a virtual server can apply an entire group of settings to affect the way that local traffic manager manages that traffic type. A virtual server can also enable session persistence for a specific traffic type. Through a virtual server, you can set up session persistence for HTTP, SSL, SIP, and MSRDP sessions, to name a few. Finally, a virtual server can apply an I-rule, which is a user-written script designed to inspect and direct individual connections in specific ways. For example, you can create an I-rule that searches the content of a TCP connection for a specific string and, if found, directs the virtual server to send the connection to a specific pool or member. To summarize, a virtual server can do the following: distribute client requests across multiple servers to balance server load, apply various behavioral settings to a specific type of traffic, enable persistence for a specific type of traffic, direct traffic according to user-written I-rules. You can use virtual servers in any of several distinct ways. Directing traffic to a load balancing pool. A standard virtual server, also known as a load balancing virtual server, directs client traffic to a load-balanced pool and is the most basic type of virtual server. When you first create the virtual server, you assigned an existing default pool to it. From then on, the virtual server automatically directs traffic to that default pool. Sharing an IP address with a VLAN node. You can set up a forwarding or layer 2 virtual server to share the same IP address as a node in an associated VLAN. To do this, you must perform some additional configuration tasks. These tasks consist of creating a VLAN group that includes the VLAN in which the node resides, assigning a self-IP address to the VLAN group, and disabling the virtual server on the relevant VLAN. Forwarding traffic to a specific destination IP address. A forwarding, or IP, virtual server is just like other virtual servers, except that a forwarding virtual server has no pool members to load balance. The virtual server simply forwards the packet directly to the destination IP address specified in the client request. When you use a forwarding virtual server to direct a request to its originally specified destination IP address, Local Traffic Manager adds, tracks, and reaps these connections just as with other virtual servers. You can also view statistics for a forwarding virtual server. Increasing the speed of processing HTTP traffic. A performance HTTP virtual server is a virtual server with which you associate a fast HTTP profile. Together, the virtual server and profile increase the speed at which the virtual server processes HTTP requests, increasing the speed of processing Layer 4 traffic. A performance or Layer 4 virtual server is a virtual server with which you associate a fast L4 profile. Together, the virtual server and profile increase the speed at which the virtual server processes Layer 4 requests. Relaying DHCP traffic. You can create a type of virtual server that relays Dynamic Host Control Protocol, or DHCP, messages between clients and servers residing on different IP networks. Known as a DHCP relay agent, a big IP system with a DHCP relay type of virtual server listens for DHCP client messages being broadcast on the subnet and then relays those messages to the DHCP server. The DHCP server then uses the big IP system to send the responses back to the DHCP client. Configuring a DHCP relay virtual server on the big IP system relieves you of the tasks of installing and running a separate DHCP server on each subnet. When you create a virtual server, you specify the pool or pools that you want to serve as the destination for any traffic coming from that virtual server. You also configure its general properties, some configuration options, and other resources you want to assign to it, such as iRules or sessions persistence types. Explain how a packet is processed once it arrives on the device. In version 4.x, which was just prior to version 9.x when TMOS was created, the big IP system used a virtual server precedence to define the order in which it routes a packet to a specific virtual server in the event that the packet matches multiple virtual server definitions. The order of virtual server precedence was, from the highest precedence to the lowest precedence, as follows: IP and port, IP or any, network and port, any and port, network, any, VLAN, port, VLAN, any. Many things have changed since then. In version 9x through 11.2.1, which is not a part of this exam version but is a building block for the current exam version, the big IP system determines the order of precedence applied to new inbound connections using an algorithm that places a higher precedence on the address net mask and a lesser emphasis on the port. Big IP LTM sets virtual server precedence according to the following criteria. The first precedent of the algorithm chooses the virtual server that has the longest subnet match for the incoming connection. If the number of bits in the subnet mask match, the algorithm chooses the virtual server that has a port match. If no port match is found, the algorithm uses the wildcard server, if a wildcard virtual server is defined. A wildcard address has a net mask length of 0. Thus, it has a lower precedence than any matching virtual server with a defined address. The algorithm results in the following order of precedence: address and port, address and any, network and port, network and any and port, any. Example of VIP precedence behavior. For example, a big IP system with the following VIPs configured on the inbound VLAN: 10.0.0.0/8:80, 10.10.0.0/16:80, 10.10.10.10/32:80, 20.0.0.0/8:80, star 20.0.0.0/8:80, *:80, alternatively noted as 0.0.0.0/0:80, or *:*, alternatively noted as any, or 0.0.0.0/0:any. There's a table listed here, and it illustrates how inbound destination addresses map to the configured VIPs. Recommend looking at the study guide for any time there's a reference to image. Changes in the order of precedence applies to new inbound connections are in version 11.3 and later, which covers the material of this exam. Complete details can be found at the following location. And there's a link for order of precedence. Starting in Big IP 11.3.0, you can configure source addresses from which virtual servers accept traffic. The Big IP system uses the destination address, source address, and service port configuration to determine the order of precedence applied to the new inbound connections. When a connection matches multiple virtual servers, the Big IP system uses an algorithm that places virtual server precedence in the following order: destination address, source address, service port. This algorithm uses the following order of precedence, and then there's a table listed here. With the addition of the source address matching on the virtual server, you can now have more than one virtual server listening on the same IP and port combination, as long as the source IP filter is different on each listener. Explain how a virtual server processes a request, and there's a link here. Standard virtual server. The Big IT LTM TMOS operating system implements full proxy architecture for virtual servers configured with a TCP profile. By assigning a custom TCP profile to the virtual server, you can configure the Big IP LTM to maintain compatibility to disparate server operating systems in the data center. At the same time, the Big IP LTM can leverage its TCP/IP stack on the client side of the connection to provide independent and optimized TCP connections to client systems. In a full proxy architecture, the Big IP LTM appears as a TCP peer to both the client and the servers by associating two independent TCP connections with the end-to-end session. Although certain client information such as the source IP address or source TCP port may be reused on the server side of the connection, the Big IP LTM system manages the two sessions independently, making itself transparent to the client and server. The standard virtual server requires a TCP or UDP profile and may optionally be configured with HTTP, FTP, or SSL profiles if Layer 7 or SSL processing is required. The TCP connection setup behavior for a standard virtual server varies depending on whether a TCP profile or a TCP and Layer 7 profile, such as HTTP, is associated with the virtual server. Standard virtual server with a TCP profile. There's a diagram listed here. Given a specific connectivity issue, isolate where the problem might be according to the processing order. GUI study in the VLabs. This blueprint topic is related to choosing the correct answer for a scenario type of question. For most questions like these, you must have exposure to supporting the Big IP platform in a production environment or understand many of the different issues that may arise around the topic and the best practice method of solving the issue. Hands-on study is the best way to master these types of topics. In general, all troubleshooting should be done in an order that allows for narrowing of the possible issue. Where there is an issue with connectivity to a virtual server, there can be many reasons. Gather what you know. When you or the client tried to connect to the virtual server, how was it done? Was it through a browser or another application? What was the path that was used? Starting out with checking to see if you have IP connectivity to the virtual server is a good place to start. This is a sort of divide and conquer approach to solve the issue. Can you reach the virtual server IP address from your location on the network? Start with a ping of the virtual server address. If you can ping the IP, we know the F5 is listening. Now, are you connecting to the port number the virtual server is listening on? If you are browsing to https www.yoursite.com, does the DNS name of www.yoursite.com resolve to the IP, the address the virtual server is configured on? If not, is it the NAT address of the firewall that translates to the virtual server address? If all the network connectivity looks good, is the virtual server configured correctly for the type of traffic that it's trying to pass? Perhaps the administrator has applied a profile to the virtual server, telling it to process HTTP traffic when the virtual server is set to listen on 443. Without terminating the SSL traffic, the virtual server cannot process HTTP traffic and the virtual server will not work correctly. These are just a few of the scenarios that you can be faced with trying to figure out why a connection to an application may not be working. Spending time on the VLabs and getting comfortable with interface and configuring virtual servers will help you understand how the Big IP LTM works. Objective 1.02. Identify the reason a virtual server is not working as expected. Determine the state of a virtual server, offline, enabled, etc. There's a link here. At any time, you can determine the status of a virtual server or virtual address using the configuration utility. You can find this information by displaying the list of virtual servers or virtual server addresses and viewing the status column, or by viewing the availability property of the object. The configuration utility indicates status by displaying one of several icons, distinguished by shape and color. The shape of the icon indicates the status that the monitor has reported for that node. The color of the icon indicates the actual status of the node. To understand these icons with respect to status, see the table below. Explanation of the status icons for virtual server and virtual addresses. And then there's a table listed here. When the indicator is a green circle, the virtual server or virtual address is enabled and ready to receive traffic. When the indicator is a yellow triangle, the virtual server or virtual address is enabled but currently unavailable. However, the virtual server or virtual address might become available later with no action required. An example of a virtual server or virtual address showing this status is when the object's connection limit has been exceeded. When the number of connections falls below the configured limit, the virtual server or virtual address becomes available again. A red diamond, the virtual server or virtual address is enabled, but offline, because an associated object has marked the virtual server or virtual address as unavailable. To change the status so that the virtual server or virtual address can receive traffic, you must actively enable the virtual server or virtual address. A black circle, the virtual server or virtual address is operational but set to disabled. To resume normal operation, you must manually enable the virtual server or virtual address. A blue square. The status of the virtual server or virtual address is unknown. Determine if a virtual server is configured with the proper IP address configuration. GUI study in the VLabs. There's a link here for that study. The blueprint topic is related to choosing the correct answer for a scenario type of question. For most questions like these, you must have exposure to supporting the Big IP platform in a production environment or understand many of the different issues that may arise around the topic and the best practice method of solving the issue. Hands-on study is the best way to master these types of topics. A virtual address is the IP address with which you associate a virtual server. For example, if a virtual server's IP address and service are 10.10.10.2:80, then the IP address 10.10.10.2 is a virtual address. You can create a many-to-one relationship between virtual servers and virtual address. For example, you can create 3 virtual servers, 10.10.10.2:80, 10.10.10.2:443, and 10.10.10.2:161 for the same virtual address of 10.10.10.2. You can enable and disable a virtual address. When you disable a virtual address, none of the virtual servers associated with that address will receive incoming network traffic. You create a virtual address indirectly when you create a virtual server. When this happens, Local Traffic Manager internally associates the virtual address with a MAC address. This in turn causes the Big IP system to respond to Address Resolution Protocol, or ARP requests for the virtual address, and to send gratuitous ARP requests and responses with respect to the virtual address. If the address you entered is not the correct address that your clients are attempting to connect to, the symptom will seem as if the Big IP is not working. This is a very common issue when DNS entries that resolve a name to the virtual server IP address do not correlate. If your clients are connecting to a DNS name, make sure that it resolves to the intended virtual server address or NAT address on the firewall that maps to the virtual server IP address. Determine if a virtual server is configured for the proper listening port. GUI study in the VLabs again. This blueprint topic is related to choosing the correct answer for a scenario type of question. For most questions like these, you must have exposure to supporting the Big IP platform in a production environment or understand many of the different issues that may arise around the topic and the best practice method of solving the issue. Hands-on study is the best way to master these types of topics. When you configure a virtual server and define the virtual server address and service port, this is how the virtual server is listening on the network. If the service port you have configured is not the appropriate port number for the type of connection that your clients are attempting to make, the connection will likely fail. Understanding how your clients intend to connect to the virtual server is usually a good sanity check on the configuration. Determine if the virtual server is configured with the appropriate profiles. There's a link here. A virtual server has a number of properties and settings that you can configure to affect the way that a virtual server manages traffic. You can also assign certain resources to a virtual server, such as load balancing pool and persistence profile. Together, these properties, settings, and resources represent the definition of a virtual server, and most have default values. When you create a virtual server, you can either retain the default values or adjust them to suit your needs. Profiles are one of the settings you can assign to a virtual server to control how the virtual server will behave. Profiles are a configuration tool that you can use to affect the behavior of certain types of network traffic. More specifically, a profile is an object that contains settings with values for controlling the behavior of a particular type of network traffic, such as HTTP connections. Profiles also provide a way for you to enable connection and session persistence and to manage client application authentication. By default, Local Traffic Manager provides you with a set of profiles that you can use as is. These default profiles contain various settings with default values that define the behavior of different types of traffic. If you want to change those values to better suit the needs of your network environment, you can create a custom profile. A custom profile is a profile derived from a default profile and contains values that you specify. You can use profiles in the following ways. You can use the default profiles, which means that you do not need to actively configure any profile settings. Local Traffic Manager uses them to automatically direct the corresponding traffic types according to the values specified in those profiles. You can use a custom profile, using the default profile as the parent profile, modifying some or all of the values defined in that profile. You can create a custom profile to use as a parent profile for other custom profiles. After configuring a profile, you associate the profile with a virtual server. The virtual server then processes traffic according to the values specified in the profile. Using profiles enhances your control over managing network traffic and makes traffic management tasks easier and more efficient. You can associate multiple profiles with a single virtual server. For example, you can associate a TCP profile, an SSO profile, and an HTTP profile with the same virtual server. How profiles are assigned to the virtual server can affect the virtual server's ability to process the traffic that is passed through it. For instance, if you create a virtual server that is listening on 10.10.10.2:443 and you also assign an HTTP profile to process the HTTP traffic according to your needs, the virtual server will not respond to connections as expected. The virtual server settings say to take an encrypted traffic on port 443 and then process and possibly manipulate the HTTP headers. This is impossible without first terminating the encrypted traffic with a client-side SSL profile to make the encrypted traffic clear text for the Big IP to then apply the HTTP profile. If you apply a visual map of the OSI model to the functional parts of the virtual server's configuration, it is easier to see what may be needed or may be conflicting with each other. This is covered in depth in the F5 certified training course. Determine if the pool configuration has an effect on virtual server state. GUI study in the VLabs. If all pool members are offline or misconfigured, the virtual server's state can be affected. All health status information trickles up to the virtual server. This means that if a node is not online due to a monitor marking the node offline, any pool member using that node will be marked offline as well. And if all members of a pool are marked offline by a failing health monitor, the virtual server will have no available resources, so it will be marked offline as well. To see if a virtual server is not available due to a lack of resources, look in the GUI under Local Traffic and click on the Network Map, Show Map, and search for the virtual server in question. If it is down, you can see in the same pane if the resources are also offline. Determine which tools to use in order to diagnose the issue. GUI study in the VLabs. This blueprint topic is related to choosing the correct answer for a scenario type question. We've heard all this before, so we'll continue. There are multiple tools you can use to check to see if a server behind the big IP is working as expected. If you have a workstation on the local server subnet, you can make a direct connection to the server to see the response. Or if you have a route to the server's IP subnet from your current network location, you can try to connect to the server directly. If it is responding, then look to see if the pool member is configured to match how you just connected to the server, IP and port. If you can see if the big IP has connectivity to the IP address of the server using the ping command from the command line interface of the big IP. If there is IP connectivity, then you can try to use a curl command to see if the big IP can connect to the website on the server, or FTP if the server is listening for FTP traffic. Explain the difference between the virtual server status definitions. Again, GUI study in the VLabs. A virtual server status icon is a quick way to see the high-level status of the virtual server. The 5 different status levels are enabled, offline, currently unavailable, unknown, and disabled. Each of these levels are pretty self-explanatory. Enabled means that the virtual server is up and available for traffic. Monitors are succeeding, and is represented by a green circle icon. Offline means that the resource for the virtual server is not available, likely a failing monitor, and is represented by a red diamond icon. Currently unavailable means that the virtual server or all of its resources have reached a restricting connection limit that has been set by the administrator, and the virtual server currently has no further capacity for traffic until the current connections fall below the connection limit settings. A yellow triangle icon represents the currently unavailable status. Unknown means that there is not any monitors set for the resources of the virtual server, so there is no status to show and is represented by a blue square icon. This status does not mean that the virtual server will not respond to traffic. A virtual server with an unknown status will take in traffic and send it on to the resources even if they are not online. Disabled means that the administrator has marked the virtual server down so that it will not process traffic. The status icon will be a shape that represents the current monitor status of the virtual server, but will always be colored black. Examples of this status icon would be, if the virtual server has succeeded monitors but is disabled, the icon would be a black circle. Or if the virtual server has failed monitors but is disabled, the icon would be a black diamond. Or if the virtual server has no monitors but is disabled, the icon would be a black square. Identify the reason a pool member has been marked down by health monitors. Pool intro, and there's a link here. In a typical client-server scenario, a client request goes to the destination IP address specified in the header of the request. For sites with a large amount of incoming traffic, the destination server can quickly become overloaded as it tries to service a large number of requests. To solve this problem, Big IP Local Traffic Manager distributes client requests to multiple servers instead of to the specific destination IP address only. You configure Local Traffic Manager to do this when you create a load balancing pool. You can enable or disable individual pool members. When you enable or disable a pool member, you indirectly set the value of the pool member's state's property in the following way. Enable sets the state property of the pool member to enabled. Disable sets the state property of the pool member to disabled. Note that the difference between a disabled pool member and a pool member that has a monitor reports as down is that a disabled pool member continues to process persistent and active connections. Conversely, a pool member reported as down processes no connections whatsoever. The status icons on the pool member list screen and properties screen indicate whether a pool member is currently enabled or disabled. Pool status. An important part of managing pools and pool members is viewing and understanding the status of a pool or pool member at any given time. The configuration utility indicates status by displaying one of several icons, distinguished by shape and color, for each pool or pool member. The shape of the icon indicates the status that the monitor has reported for that pool or pool member. For example, a circle-shaped icon indicates that the monitor has reported that the pool member is being as up, whereas a diamond-shaped icon indicates that the monitor has reported the pool member being down. The color of the icon indicates the actual status of the node itself. For example, a green shape indicates that the node is up, whereas a red shape indicates that the node is down. A black shape indicates that user intervention is required. At any time, you can determine the status of a pool. The status of a pool is based solely on the status of its members. Using the configuration utility, you can find this information by viewing the available property of the pool. You can also find this information by displaying the list of pools and checking the status column. The configuration utility indicates pool status by displaying one of several icons, distinguished by shape and color. To understand these icons, see table below. Explanation of status indicators for pools. And there's a table listed here. If the status indicator is a green circle, at least one pool member is available for processing traffic. If it's a yellow triangle, no pool members are currently available, but any one of them could become available later with no user action required. An example of an available pool member becoming available automatically is when the number of concurrent connections to the pool member no longer exceeds the value defined in the pool member's connection limit setting. A red diamond. All pool members are unavailable and therefore cannot accept traffic. A reason for a pool member being unavailable is that an associated EAV monitor has detected that the pool member is unavailable. When pool status is red, user action is usually required. A blue square. The status of at least one pool member is unknown, and no other pool members are available. Sample reasons for unknown pool member status are: one or more pool members has no associated monitor. Monitor results are not available yet. The pool member's IP address is misconfigured. The parent node has been disconnected from the network. Discuss the effects of health monitors on the status of pool members and nodes. There's a link here. Health monitors are a key feature of Local Traffic Manager. Health monitors help to ensure that a server is in an up state and able to receive traffic. When you want to associate a monitor with an entire pool of servers, you do not need to explicitly associate the monitor with each individual server. Instead, you can simply assign the monitor to the pool itself. Local Traffic Manager then automatically monitors each pool member of the pool. Local Traffic Manager contains many different pre-configured monitors that you can associate with pools, depending on the type of traffic you want to monitor. You can also create your own custom monitors and associate them with pools. The only monitor types that are not available for associating with pools are monitors that are specifically designed to monitor nodes and not pools or pool members. That is, the destination address in the monitor specifies an IP address only rather than an IP address in a service port. These monitor types are ICMP, TCP Echo, Real Server, SNMP DCA, SNMP DCA Base, and WMI. With Local Traffic Manager, you can configure your monitor associations in many useful ways. You can associate a health monitor with an entire pool instead of an individual server. In this case, Local Traffic Manager automatically associates that monitor with all pool members, including those that you add later. Similarly, when you remove a member from a pool, Local Traffic Manager no longer monitors that server. When a server that is designated as a pool member allows multiple processes to exist on the same IP address and port, you can check the health or status of each process. To do this, you can add the server to multiple pools, and then within each pool, associate a monitor with that server. The monitor you associate with each server checks the health of the process running on that server. When associating a monitor with an entire pool, you can exclude an individual pool member from being associated with that monitor. In this case, you can associate a different monitor for that particular pool member, or you can exclude that pool member from health monitoring altogether. For example, you can associate pool members A, B, and D with the HTTP monitor, while you associate member C with the HTTPS monitor. You can associate multiple monitors with the same pool. For instance, you can associate both HTTP and HTTPS monitors within the same pool. Determine the state and availability of the pool member or node in question. There's a link here, and then there's a table. Explanation of status icons for pool members. A green circle. The pool member is set to enabled, the parent node is up, and the monitor has marked the pool member as up. The property state is set to enabled, or all traffic allowed. A yellow triangle. The pool member is unavailable, but could become available later with no user interaction required. This status occurs when the number of concurrent connections has exceeded the limit defined in the pool member's connection limit setting. The state of the property is set to enabled, or all traffic allowed. A red diamond. The pool member is unavailable because either the parent node is down, a monitor has marked the pool member as down, or a user has disabled the pool member. The state property is set to enabled, or all traffic allowed. A black circle. The pool member is set to disabled, although a monitor has marked the pool member as up. To resume normal operation, you must manually enable the pool member. The state the property is set to is disabled, only persistent or active connections allowed. A black circle. The pool member is set to disabled and is offline because the parent node is down. To resume normal operation, you must manually enable the pool member. The state the property is set to is forced offline, only active connections allowed. A black diamond. The pool member is set to disabled and is offline because a user has disabled it. To resume normal operation, you must manually enable the pool member. The state the property is set to is disabled, only persistent or active connections allowed. Another black diamond. The pool member is set to disabled and is offline because either the parent node is down or a monitor has marked the pool member as down. To resume normal operation, you must manually enable the pool member. The state the property is set to is forced offline, only active connections allowed. A blue square. The pool member or node has no monitor associated with it or no monitor results are available yet. The state the property is set to is enabled or all traffic allowed. Verify pool member or node ratio configuration. There's a link here. Ratio weights for pool members. When using a ratio-based load balancing method for distributing traffic to servers within a pool, you can assign a ratio weight to the corresponding pool members. The ratio weight is used by the local traffic manager to distribute connections among pool members or nodes in a static rotation. The number of connections that each system receives over time is proportionate to the ratio weight you define for each pool member or node. The ratio-based load balancing methods are ratio, node, member, and sessions, dynamic ratio, node, member, and ratio least connections, node, and member. Verify the pool member or node connection configuration and count. You can configure a virtual server, pool member, or node to prevent an excessive number of connection requests during events such as a denial of service attack or a planned high-demand traffic event. To ensure the availability of a virtual server, pool member, or node, you can use the Big IP Local Traffic Manager to manage the total number of connections and the rate at which connections are made. When you specify a connection limit, the system prevents the total number of concurrent connections to the virtual server, pool member, or node from exceeding the specified number. When you specify a connection rate limit, the system controls the number of allowed new connections per second, thus providing a manageable increase in connections without compromising availability. After configuring connection limits and connection rate limits on a virtual server, or after configuring these limits on a pool member or node associated with the virtual server, the system controls the total number of concurrent connections and the rate of new connections to the virtual server, pool member, or node. Objective 1.04. Identifying a pool member not in the active priority group. Identify a pool member not in the active priority group, and there's a link here. About priority-based member activation. Priority-based member activation is a feature that allows you to categorize pool members into priority groups so that pool members in higher priority groups accept traffic before pool members in lower priority groups. The priority-based member activation feature has two configuration settings. Priority group activation. For the priority group activation setting, you specify the minimum number of members that must remain available in each priority group in order for traffic to remain confined to that group. The allowed value for this setting ranges from 0 to 65535. Setting this value to 0 disables the feature, equivalent to using the default value of disabled. Priority group. When you enable priority group activation, you also specify a priority group for each member when you add that member to the pool. Retaining the default priority group value of 0 for a pool member means that the pool member is in the lowest priority group and only receives traffic when all pool members in higher priority groups are unavailable. If the number of available members assigned to the highest priority group drops below the number that you specify, the Big IP system distributes traffic to the next highest priority group, and so on. For example, this configuration has 3 priority groups, 3, 2, and 1, with the priority group activation values shown here as minimum active members set to 2. Pool, my pool, LB mode fastest, min active members 2, member 10, 12, 10, 7, 80 priority 3, member 10, 12, 10, 8, 80 priority 3, member 10, 12, 10, 9, 80 priority 3, 10, 12, 10, 4, 80 priority 2, 10, 12, 10, 5, 80 priority 2, 10, 12, 10, 6, 80 priority 2, 10.12.10.1 80 priority 1, 10.12.10.2 priority 1, 10.12.10.3 priority 1. Connections are first distributed to all pool members within priority 3, the highest priority group. If fewer than 2 priority 3 members are available, traffic is directed to the priority 2 members as well. If both the priority 3 group and the priority 2 group have fewer than 2 members available, traffic is directed to the priority 1 group. The Big IP system continuously monitors priority groups, and wherever a higher priority group once again has the minimum number of available members, the Big IP system limits traffic to that group. To see which pool members are not receiving traffic, you can look at statistics in the GUI or on console. Objective 1.05, Pre-persistence. Explain the concept of persistence. Due to the 201 exam blueprint having an obvious mistake with layout or objectives, I have added this section. And there is a link here. Using Big IP Local Traffic Manager, you can configure session persistence. When you configure session persistence, Local Traffic Manager tracks and stores session data, such as the specific pool member that serviced a client request. The primary reason for tracking and storing session data is to ensure that client requests are directed to the same pool member throughout the life of a session or during a subsequent session when an application requires it to be so. In addition, session persistence can track and store other types of information, such as user preferences or a username and password. Local Traffic Manager offers several types of session persistence, each one designed to accommodate a specific type of storage requirement for session data. The type of persistence that you implement depends on where and how you want to store client-specific information, such as items in a shopping cart or airline ticket reservations. For example, you might store airline ticket reservation information in a back-end database that all servers can access, or on a specific server to which the client originally connected, or in a cookie on the client's machine. When you enable persistence, returning connections will not be load balanced and instead will be sent to the server to which they last connected in order to access application. Local Traffic Manager keeps session data for a period of time that you specify. The primary tool for configuring session persistence is to configure a persistence profile and assign it to a virtual server. If you want to enable persistence for specific types of traffic only, as opposed to all traffic passing through the virtual server, you can write an I rule. To configure and manage persistence profiles, log into the Big IP configuration utility, and on the main tab, expand local traffic and click Persistence. Pre-verify the type of persistence profile assigned to the virtual server in question, and there's a link here. A persistence profile is a pre-configured object that automatically enables persistence when you assign the profile to a virtual server. By using a persistence profile, you avoid having to write a program to implement a type of persistence. Each type of persistence that Local Traffic Manager offers includes a corresponding default persistence profile. These persistence profiles each contain settings and setting values that define the behavior of the Big IP system for that type of persistence. You can either use the default profile or create a custom profile based on the default. Persistent profile types. You can configure persistence profile settings to set up session persistence on the Big IP system. You can configure these settings when you create a profile or after profile creation by modifying the profile settings. The persistence types that you can enable using a persistence profile are cookie persistence. Cookie persistence uses an HTTP cookie stored on a client's computer to allow the client to reconnect to the same server previously visited at a website. Destination address affinity persistence, also known as sticky persistence. Destination address affinity persistence supports TCP and UDP protocols and directs session requests to the same server based solely on the destination IP address of a packet. Hash persistence. Hash persistence allows you to create a persistence hash based on an existing I rule. Microsoft Remote Desktop Protocol persistence. Microsoft Remote Desktop Protocol, or MSRDP, persistence tracks sessions between clients and servers running the Microsoft Remote Desktop Protocol, RDP, service. SIP persistence. SIP persistence is a type of persistence used for servers that receive Session Initiation Protocol, SIP, messages through UDP, SCTP, or TCP. Source Address Affinity Persistence, also known as Simple Persistence. Source Address Affinity Persistence supports TCP and UDP protocols and directs session requests to the same server based solely on the source IP address of a packet. SSL Persistence. SSL persistence is a type of persistence that tracks non-terminated SSL sessions using the SSL session ID. Even when the client's IP address changes, Local Traffic Manager still recognizes the connection as being persistent based on the session ID. Note that the term non-terminated SSL sessions refers to sessions in which Local Traffic Manager does not perform the tasks of SSL certificate authentication and encryption or re-encryption. Universal persistence. Universal persistence allows you to write an expression that defines what to persist on in a packet. The expression, written using the same expression syntax that you use in iRules, defines some sequence of bytes to use as a session identifier. You can see the types of persistence assigned to a virtual server by going to Local Traffic Virtual Servers in the GUI and selecting the virtual server from the list you wish to inspect. Click on the Resources tab and look at the settings for the default persistence profile setting and the fallback persistence profile setting. To change the setting, you can select the name of the profile you created or wish to use, such as cookie. This implements cookie persistence using the default cookie persistence profile. And there's a screenshot here. Differentiate between fallback and primary persistence. GUI study in the VLabs. The administrator of a big IP can set a primary persistence type for a virtual server as shown in the previous section. A fallback persistence type can also be set. Only IP address-based persistence types are allowed as fallback. This means that along with honoring the primary persistence method, there is a second record being kept that can be used to persist the client's transaction to the resource of the virtual server as well. For example, if cookie persistence is set with a fallback of source address, as a client makes their second connection to the virtual server, the cookie from the first connection will be used to determine the server in the pool to send the connection to. But at the same time as the first connection was made to the virtual server, a source address persistence record was also created. And if the client did not have the cookie any longer, the record matching their IP address would still exist, if it had not timed out, and could be used to get them back to their original pool member. However, this also means that if a source address persistence profile is used as a fallback that has a wider subnet in the configuration, such as 255.255.255.0, and a second client from the same Class C network as the first client made their connection to the virtual server, they would be persisted to the same pool member as the first client, since they would match the source IP record of the first client even though they did not have a cookie when they connected. Pre-validate the expected persistence behavior. GUI study in the VLabs, Module 8 exercises. As you connect to an application through the virtual server of the Big IP platform, the first connection is load balanced to the best available resource according to the load balancing algorithm. With persistence enabled, the following connections from the same client will be sent to the same resource as their first initial load balanced connection. Checking to see if the client is being persistent is simple in a test scenario where a single client connects to the virtual server, and the statistics on the system show the connections only going to the same resources in the pool. However, in regular production volume, it will be hard to see the individual client connections hitting the same resource when there are hundreds or thousands of connections coming in all the time. An easy way to see that the client is connecting to the same server resource is to have watermarks on the application pages. These watermarks will show a unique mark on the web page identifying it to the individual server, much like we use in the VLabs on the load balance sites. Not all developers will take the time or effort to do this watermarking. If you do not have the ability to add a watermark to your page, then there needs to be another method. In the Big IP platform, you have the ability to show the active connection table and use filters to show the data you want to see. So to show a client's current connection to the connection table, you can type the following command. In version 9 and 10, bigpipe con show grep client IP. In version 11, TMSH show syscon CS client address client IP. Use the appropriate tool to troubleshoot persistence. GUI study in the VLabs. If the persistence method you are using is not tracked by the Big IP system, such as cookie persistence, then there are no local records on the Big IP to review. This is due to the fact that the cookie containing the pool member info is passed to the client system from the Big IP, and when the client makes the next connection, it will include the cookie from the previous in the request for the Big IP system to use for the persistence info. Allowing the Big IP to simply read the cookie and not have to locally store the info. An administrator can find the cookie on the client's workstation. It is stored where the client's local browser would normally store cookies. The location will vary by browser type and OS type. If the persistence method you are using is tracked by the Big IP system locally, such as source address affinity persistence, then you can look at the records that are stored in the local system using the following methods. Source address persistence records can be found in the configuration utility. Open the statistics, module statistics, local traffic page, and select persistence records from the statistics type list. In version 11, command line do TMSH show LTM persistence persist records. In version 9 and 10, command line do B persist show all. Objective 105, identify traffic diverted due to persistence record. Identify traffic diverted due to persistence record. When traffic matches an existing persistence record, the load balancing decision is not made for that traffic. The decision of which server to send it to has been made for that traffic by first inbound connection to the virtual server that created the record, and now the matching traffic will use that decision until the persistence record expires. You can see the existing persistence records for the methods that are kept on the system by typing the following command. Show LTM persistence persist records, or by going to Overview, Module Statistics, and choosing Persistence Records in the Statistics type field. And there's a screenshot here. Objective 106. Identify the current configured state of the pool member. There's a link here. About pool member state. You can enable or disable individual pool members. When you enable or disable a pool member, you indirectly set the value of the pool member's state property in the following way. Enable sets the state property of the pool member to enabled. Disable sets the state property of the pool member to disabled. Note that the difference between a disabled pool member and a pool member that a monitor reports as down is that a disabled pool member continues to process persistent and active connections. Conversely, a pool member reported as down processes no connections whatsoever. The status icons on the pool member list screen and properties screen indicate whether a pool member is currently enabled or disabled. Pool and pool member status. An important part of managing pools and pool members is viewing and understanding the status of a pool or pool member at any given time. The configuration utility indicates status by displaying one of several icons distinguished by shape and color for each pool or pool member. The shape of the icon indicates the status that the pool monitor has reported for that pool or pool member. For example, a circle-shaped icon indicates that the monitor has reported the pool member as being up, whereas a diamond-shaped icon indicates that the pool monitor has reported the pool member as being down. The color of the icon indicates the actual status of the node itself. For example, a green shape indicates that the node is up, whereas a red shape indicates that the node is down. A black shape indicates that user intervention is required. At any time, you can determine the status of a pool. The status of a pool is based solely on the status of its members. Using the configuration utility, you can find this information by viewing the available property of the pool. You can also find this information by displaying the list of pools and checking the status column. You can see the status of a pool member in the GUI by going to Local Traffic, Pools, and clicking on the pool you want to see. Navigate to the Members tab to view each pool member's status. You can click on the pool member to see which monitor may have changed the status of the pool member. And there's a screenshot here. Objective 1.07. Identify a persistence issue. General Network Study and VLabs. This blueprint topic is related to choosing the correct answer for a scenario type of question. For most questions like these, you must have exposure to supporting the Big IP platform in a production environment or understand many of the different issues that may arise around the topic and the best practice method of solving the issue. Hands-on study is the best way to master these types of topics. When there is a persistence issue, a user's session state data will not be available to the user's session, and it could result in many different issues. If they are connecting to an application that requires a login, and they are load balanced to a different server after they have logged in for their first connection, they may be presented with the login screen for the next server. If they are using a website filling out an online form or filling up their shopping cart with items and they are load balanced to a different server, their form data or cart contents may not be available to that next server's session. A simple fix for most session state issues is to turn on persistence on the Big IP platform and not load balance every session, only a user's first connection. However, even though we can generally fix the issue and the real problem lies with the application not sharing session state between the servers. If the necessary information is shared between the application servers, we would be able to load balance every connection to the most available server. Most of time cost is the issue because it can be expensive to run a session state database or to rewrite the application to handle it. Issues. Objective 2.01. Perform an end-user diagnostic per F5 documentation and collect the output. Reboot an F5 platform into the EUD, and there's a link here. You can run the EUD only from a console connected to the Big IP system. You can start the EUD using the following methods. Attach a USB CD-ROM drive containing the bootable system CD. As the system boots up, the EUD starts. Attach a USB mass storage device drive with the EUD boot image loaded. As the system boots up, the EUD starts. When the system is booting, select the End User Diagnostics option from the boot menu. You can then run the tests that are necessary. After you have completed the tests you want to run, use option 21 to exit the EUD and reboot the system. You must use this option to exit the EUD. Using other methods such as rebooting or using the command menu can destabilize the system. Download output from the unit an EUD was run on, and there's a link here as well. An end-user diagnostic, or EUD, report log is stored as a text file named eud.log in the shared log directory on the host file system. If you have run an EUD test on the system, it will be available in this location. You can connect to the console IP address of the Big IP system and use the SCP tool to get the file off the system to upload to the F5 support case. Interpret the output from an EUD and determine if the test passed or failed. There's a link here as well. When all tests complete correctly, the following message displays: completed test with 0 errors. Interpret the LCD warning messages. Locate the LCD on an F5 platform. There's a link here. On the front panel of the platform, you can reset the unit using the LCD control buttons. You can also use the front panel LEDs to assess the condition of the platform. On the back, you can power off the unit. Front view of the platform. There's a diagram here showing all of the various parts listed as management port, USB ports, console serial port, serial or hardwired failover port, 10100, 1000 interfaces, 1 gig, 10 gig optical ports, indicator LEDs, LCD display, and LCD control buttons. The liquid crystal display, or LCD panel, provides the ability to control the unit without attaching a console or network cable. The LCD panel is located on the front of all F5 hardware except for the Viprion 2400 series chassis. A separate USB attachable LCD panel is available for the Viprion 2400 series chassis. Correlate the LCD message to message in the corresponding log files. And there's a link here. Alert conditions. Alerts that affect the behavior of the alarm LED indicator are defined in the etc alertd alert.conf file. The LCD warn function of an alert definition defines which alerts will modify the alarm LED indicator. As an example, the default alertd process conditions in Big IP version 9.2 are defined in the following table, and then there's a table listed with some descriptions, alert levels, and LED behaviors. The events that trigger LCD screen events and lights are written to log files. You may want to look up more information on the logged events. For example, the Big IP system may generate an error message to the var log LTM file that contains the following event. Identify which tasks the buttons on the LCD perform. There's a link. Pressing the X button puts the LCD panel in menu. The buttons left arrow, right arrow, up arrow, and down arrow are only functional when the LCD is in the menu mode for navigation. The X check button is used to select and confirm selections. Refer to the hyperlink to review the menu options available on the LCD panel. Identify a possible hardware issue within the log files, Objective 2.03. Indicate which logs would contain debugging information, and there's a link here. If you are using the syslog utility for local logging, whether or not you are using the high-speed logging mechanism, you can view and manage the log messages using the Big IP configuration utility. The local syslog logs that the Big IP system can generate include several types of information. For example, some logs show a timestamp, hostname, and service for each event. Moreover, logs sometimes include a status code, while the audit log shows a username and a transaction ID corresponding to each configuration change. All logs contain a one-line description of each event. For local log messages that the Big IP system stores in the local syslog database, the Big IP system automatically stores and displays log messages in these categories: system messages, packet filter messages, local traffic messages, global traffic messages, Big IP system configuration or audit messages. Each type of event is stored locally in a separate log file, and the information stored in each log file varies depending on the event type. All log files for these event types are in the directory var log. The product-specific logs like var log LTM, var log GTM, etc. will contain debug info relative to that product. If you are logging from an iRule, you can define what log file you want to write your debug info into by specifying the local facility you choose. Given a log file, determine the nature of a hardware issue. And there's a link. This blueprint topic is related to choosing the correct answer for a scenario type question. For most questions like these, etc., etc. Continuing. You may look in the logs and see there are many events. Perhaps you notice an event like this. And then there's an event listed, essentially link 2.5 is up. This could have been caused by the administrator turning up a new interface or because the interface lost connectivity to the upstream switch. Some events can be self-explanatory, while others may be more cryptic and need more deciphering. Understanding log content. The logs that the Big IP system generates include several types of information. For example, some logs show a timestamp, hostname, and service for each event. Moreover, logs sometimes include a status code, while the audit log shows a username and a transaction ID corresponding to each configuration change. All logs contain a one-line description of each event. The table below lists the categories of information contained in the logs and the specific logs in which the information is displayed. And there's a table listed here that you should take a look at. 2.03. Given a possible issue, determine which log file entries to review. Viewing and managing log messages are an important part of maintaining a Big IP system. Log messages inform you on a regular basis of the events that are happening on the system. Some of these events pertain to general events happening within the operating system, while other events are specific to the Big IP system, such as the stopping and starting of Big IP system services. The mechanism that the Big IP system uses to log events in the Linux utility syslog-ng. This syslog-ng utility is an enhanced version of the standard Unix and Linux logging utility syslog. The types of events that the Big IP system logs are system events, which are system event messages based on Linux events and are not specific to the Big IP system. Packet filter events. Packet filter messages are those that result from the implementation of packet filters and packet filter rules. Local traffic events. Local traffic event messages pertain specifically to the local traffic management system. Audit events. Audit event messages are those that the Big IP system logs as a result of changes to the Big IP system configuration. Logging audit events is optional. To configure and manage event logging, log into the Big IP configuration utility, and on the main tab, expand System and click Logs. As described in introducing Big IP system logging, the Big IP system automatically logs 4 main event types: system, packet filter, local traffic, and configuration changes or audit. Each type of event is stored in a separate log file, and the information stored in each log file varies depending on the event type. All log files for these event types are in the directory var log. Logging system events. Many events occur on the Big IP system that are Linux-related events and do not specifically apply to the Big IP system. Using the configuration utility, you can display these system messages. The table below shows some sample system log entries. Sample system log entries. And there's a table listed here, which you should take a look at. Logging packet filter events. Some of the events on the Big IP system logs are related to packet filtering. The system logs the messages for these events in the file var log pkt filter. Using the configuration utility, you can display these packet filter messages. Logging local traffic events. Many of the events that the Big IP system logs are related to local area traffic passing through the Big IP system. The Big IP system logs the messages for these events in the file var log LTM. Using the configuration utility, you can display these local traffic messages. The table below shows some sample local traffic log entries. Sample local traffic log entries, and there is a table here that you should take a look at. Some of the specific types of events that the Big IP system displays in the local traffic logging screen are address resolution protocol or ARP packet and ARP cache events, BigDB database events such as populating and persisting BigDB variables, HTTP protocol events, HTTP compression events, IP packet discard events due to exceptional circumstances or invalid parameters such as a bad checksum, Layer 4 events, events related to TCP, UDP, and FastL4 processing, MCP or TMM configuration events, monitor configuration events, network layer events, layers 1 and 2, packet velocity or ASIC PVA configuration events, iRule events related to runtime iRule processing, SSL traffic processing events, and general TMM events such as TMM startup and shutdown. Objective 2.04. Force an active unit to standby under the appropriate circumstances. Force an active unit to standby under the appropriate circumstances. General network study and VLabs. This blueprint topic, etc., etc. And continuing, for example, if the Big IP HA pair is synchronized, then the configurations are the same on both systems. If the active system is having an issue and you can't find an issue with the other systems in the environment, client or server, the issue may have something to do with the LTM. You could try a failover of the active system to the standby system. If the problem resolves, then you are likely faced with an issue in the first system, and since they were in sync, it may be hardware. That hardware issue may be in the LTM or in the network systems that it is connected to. If the failover did not solve the issue, the problem is likely a configuration issue and the hardware has probably been eliminated. Since a failover of an HA pair can interrupt current connections of clients, and depending on the type of connection they may have made, their connection may not recover from the termination of the connection, if connection mirroring is not properly configured for long-lived connections. Using failover as a troubleshooting step should be done as a last measure. However, it can help to narrow down if there is an issue with hardware. For a failover between systems in an HA pair, to be transparent to the clients currently connected to the active unit, the state of the active connections needs to be known by the standby system. If the connection states are not known by the standby system when the failover occurs, connections that were just being persisted, connections that were being snatted, or any other active connection state known by the active unit will not survive the failover. To create a stateful failover environment, the systems must be configured to mirror the current connection table, persistence records and SNAT table to the standby unit. Objective 2.05. Understand the relationship between interfaces, trunks, VLANs, and their status and statistics. There's a link here. Introduction to Big IP System Interfaces. A key task of the Big IP System configuration is the configuration of Big IP System interfaces. The interfaces on a Big IP system are the physical ports that you use to connect the Big IP system to other devices on the network. These other devices can be next hop routers, layer 2 devices, destination servers, and so on. Through its interfaces, the Big IP system can forward traffic to or from other network devices. Note, the term interface refers to the physical ports on the Big IP system. Every Big IP system includes multiple interfaces. The exact number of interfaces that you have on the Big IP system depends on the platform type. A Big IP system has two types of interfaces. A management interface. The management interface is a special interface dedicated to performing a specific set of system management functions. TMM switch interfaces. TMM switch interfaces are those interfaces that the Big IP system uses to send or receive application traffic, that is, traffic slated for application delivery. Each of the interfaces on the Big IP system has unique properties, such as the MAC address, media speed, duplex mode, and support for link layer discovery protocol, or LLDP. In addition to configuring interface properties, you can implement a feature known as interface mirroring, which you can use to duplicate traffic from one or more interfaces to another. You can also view statistics about the traffic on each interface. Once you have configured the properties of each interface, you can configure several other features of the Big IP system that control the way that interface operates. For example, by creating a virtual local area network, or VLAN, and assigning interfaces to it, the Big IP system can insert a VLAN ID or tag into frames passing through those interfaces. In this way, a single interface can forward traffic from multiple VLANs. Introduction to Virtual LANs. A VLAN is a logical subset of hosts on a local area network, or LAN, that operate in the same IP address space. Grouping hosts together in a VLAN has distinct advantages. For example, with VLANs, you can reduce the size of broadcast domains, thereby enhancing overall network performance, reduce system and network maintenance tasks substantially. Functionally related hosts no longer need physically reside together to achieve optimal network performance, enhance security on your network by segmenting hosts that must transmit sensitive data. The way that you group hosts into VLANs is by using the configuration utility to create a VLAN, and associate physical interfaces with that VLAN. In this way, any host that sends traffic to a Big IP system interface is logically a member of the VLAN or VLANs to which that interface belongs. And there's a link here. VLANs on a Big IP system. The Big IP system is a port-based switch that includes multi-layer processing capabilities. These capabilities enhance standard VLAN behavior in these ways. You can associate physical interfaces on the Big IP system directly with VLANs. In this way, you can associate multiple interfaces with a single VLAN, or you can associate a single interface with multiple VLANs. You do not need physical routers to establish communication between separate VLANs. Instead, the Big IP system can process messages between VLANs. You can incorporate Big IP system into existing multi-vendor switched environments due to the Big IP system's compliance with the IEEE 8021Q VLAN standard. You can combine two or more VLANs into an object known as a VLAN group. With a VLAN group, a host in one VLAN can communicate with a host in another VLAN using a combination of Layer 2 forwarding and IP routing. This offers both performance and reliability benefits, and there's a link here. Introduction to trunks. A trunk is a logical grouping of interfaces on the Big IP system. When you create a trunk, this logical group of interfaces functions as a single interface. The Big IP system uses a trunk to distribute traffic across multiple links in a process known as link aggregation. With link aggregation, a trunk increases the bandwidth of a link by adding the bandwidth of multiple links together. For example, four fast Ethernet or 100 Mbps links, if aggregated, create a single 400 Mbps link. With one trunk, you can aggregate a maximum of 8 links. For optimal performance, you should aggregate links in powers of 2. Thus, you ideally aggregate 2, 4, or 8 links. The purpose of a trunk is twofold: to increase bandwidth without upgrading hardware, to provide link failover if a member link becomes unavailable. You can use trunks to transmit traffic from a Big IP system to another vendor switch. Two systems that use trunks to exchange frames are known as peer systems. How do trunks work? In a typical configuration where trunks are configured, the member links of the trunk are connected through Ethernet cables to corresponding links on a peer system. This figure shows an example of a typical trunk configuration with 2 peers and 3 member links on each peer. And then there's a diagram shown here. A primary goal of the trunks feature is to ensure that frames exchanged between peer systems are never sent out of order or duplicated on the receiving end. The Big IP system is able to maintain frame order by using the source and destination addresses in each frame to calculate a hash value, and then transmitting all frames with that hash value on the same member link. The Big IP system automatically assigns a unique MAC address to a trunk. However, by default, the MAC address that the system uses as the source and destination address for frames that the system transmits and receives, respectively, is the MAC address of the lowest numbered interface of the trunk. The Big IP system also uses the lowest numbered interface of a trunk as a reference link. The Big IP system uses the reference link to take certain aggregation actions, such as implementing the automatic link selection policy. For frames coming into the reference link, the Big IP system load balances the frames across all member links that the Big IP system knows to be available. For frames going from any link in the trunk to a destination host, the Big IP system treats those frames as if they came from the reference link. Finally, the Big IP system uses the MAC address of an individual member link and the source address for any LACP control frames. Overview of LACP. A key aspect of trunks is Link Aggregation Control Protocol, or LACP. Defined by IEEE Standard 802.3 AD, LACP is a protocol that detects error conditions on member links and redistributes traffic to other member links, thus preventing any loss of traffic on the failed link. On a big IP system, LACP is an optional feature that you can configure. You can also customize LACP behavior. For example, you can specify the way that LACP communicates its control messages from the big IP system to a peer system. You can also specify the rate at which the peer system sends LACP packets to the big IP system. If you want to affect the way that the big IP system chooses links for link aggregation, you can specify a link control policy. Section 3. Troubleshoot basic performance issues. Objective 3.01. Recognize when a packet capture is needed within the context of a performance issue. A packet capture can be one of the most powerful tools that an administrator has at their command. If you are not used to doing packet captures or have never done one, you should do them in your VLabs as soon as possible to start becoming proficient. Running TCP dump on a busy system. Important. The big IP system is designed as an application delivery network platform and not as a packet capture device. If you intend to capture traffic under high load conditions, F5 recommends mirroring traffic to a dedicated sniffing device. Running TCP dump on a big IP system is considered best effort, as it will place more load on the CPU and may result in inaccuracies in the TCP dump output, such as missed packets or packet timestamp irregularities. If you run a TCP dump on a heavily loaded big IP system, the packet capture process may not capture all matching traffic, and the statistical values reported by TCP dump may be inaccurate. If you run TCP dump on a heavily loaded system, F5 recommends using TCP dump filter expressions to mitigate the potential for missed packets. Determine an appropriate location to take the capture. And there's a link here. An administrator can also do a capture from their workstation. They will gather traffic between the destination and their workstation, which in most cases is between the virtual server on the LTM and their workstation. Captures can also be done locally on the big IP system. Doing a capture on the big IP LTM is very strategic since you have the ability to capture both sides of the proxied conversation between the workstation and the backend server resources. Understanding which networks the resources are on for both sides of the conversation will also allow you to narrow the capture using filters in the TCP dump. F5 recommends that you run TCP dump on a VLAN when you intend to capture traffic for in-depth troubleshooting on the big IP system. When the VLAN is specified in the TCP dump syntax, TCP dump can read packets processed by TMM. Determine the appropriate time to take capture. Command line study in the VLabs. The right time to do a capture can be a catch-22. You need to capture the issue, so a capture needs to be done when the problem is occurring. Of course, sometimes the problem may only be occurring under peak load, so doing a capture during peak load may be ineffective due to issues mentioned in the opening of this section. However, most of the time, you can do the capture when the problem is occurring, and tightening up the amount of data you capture by using filters will help the overhead. Given a scenario, determine whether a packet capture is appropriate. Command line study in the VLabs. This blueprint topic is related to choosing the correct answer for a scenario type of question, etc., etc. Hands-on study. There may be times that determining the source of an issue will not require the administrator to do a capture. When a problem arises, look first to the status of the big IP and the configuration. If all of the settings and statistics look fine, you can then check the client settings and client access restrictions before moving on to a capture of the network traffic. Objective 3.02. Use big IP tools in order to identify potential performance issues. Differentiate between performance issues types, i.e. latency, congestion, or broken content. General network study. This blueprint topic is related to choosing the correct answer for a scenario type question, hands-on study, etc. Latency. Latency is the largest cause of slow web applications over the WAN or Internet. Latency describes the time delay experienced when a data packet moves from one point to another, usually caused by physical distance and high round-trip times. Latency can also be introduced by compute-intensive processes such as SSL handshaking, bulk encryption or decryption, and TCP session management. Latency can have a profound effect on application performance, even over networks with abundant bandwidth. Congestion. Network congestion occurs. A node or network is processing so much data that its level of service deteriorates. The Big IP platform has some built-in optimizations to help with network congestion. The TCP profile has a setting to enable Nagel's algorithm. Nagel's algorithm attempts to reduce network congestion by aggregating smaller TCP packets into larger ones. 3.02. Establish the frequency of a given issue, random, continuous, isolated, intermittent, or repetitive intervals. General network study. The blueprint topic is related to choosing a scenario type question answer, and hands-on study is recommended. Tracking how often issues occur or for how long an issue is impacting a function can be a telltale sign to what may be happening. This can be done through the use of logs, statistics, network captures, and observation. For instance, an administrator wants to load balance a server that is already functioning in their DMZ. They spin up a second instance of the server and place both the new and old server behind an LTM pair off of the DMZ. They use the server's address on the DMZ network for the virtual server address on the LTM and place the servers on a new network behind the LTM, with the LTM acting as the server's default gateway. The firewall administrators add the new server IP addresses to the rule sets, allowing all the same server traffic to get to the servers on the new network. When the servers are brought online, the users immediately notice a delay in the transactions to the server. It seems to be taking about 30 seconds longer than before and is consistent on every transaction. In thinking through the change in architecture, you would not expect that the F5 platform introduced a 30-second delay with each connection. The time it takes for a DNS query to time out in many systems is around 30 seconds. On a deeper look into the logs on the server, it was doing a DNS reverse lookup and it was timing out. The firewall admin had not added the new network to the DNS rule on the firewall rule to allow the network nodes to query their DNS servers. 3.02. Explain how to get performance statistics in addition to those shown in the dashboard. Overview performance. GUI study in the VLabs. To see additional platform performance information, use the following steps. In version 11 of the Big IP configuration utility, click Statistics and then click Performance. In version 10 of the Big IP configuration utility, click Overview and then click Performance. All categories are shown under the All tab, or you can see the breakouts of System, Connections, Throughput, and Cache. Section 4. Troubleshoot Basic Device Management Connectivity Issues. Objective 4.01. Verify remote connectivity to the box in order to determine the cause of a management connectivity issue. Isolate potential causes of a basic network connectivity issues given scenarios related to client configuration, client network access, device network access, and network topologies. Again, this is recommended that you get some hands-on study in order to master these topics. A general knowledge of how devices communicate on IP-based networks and basic configuration settings that are necessary on the client as well as the server environments are critical to being able to support an ADN environment. An understanding of how networks are designed and where devices are connected in a network topology are also critical to supporting an ADN environment. Apply connectivity troubleshooting tools, i.e. ping, traceroute, HTTP, HTTPS availability, remote shell access, network-based console access, in the appropriate situation. Again, the study guide recommends hands-on study in the VLabs. Understanding each of these tools' functions and when you should use them to do troubleshooting of issues is a key administration of any network. An understanding of ways to connect to systems via console to test connectivity from the remote device on the network is critical as well. Ping. Ping is a computer network administration utility used to test the reachability of a host on an Internet Protocol or IP network and to measure the round-trip time for messages sent from the originating host to a destination computer. Ping operates by sending Internet Control Message Protocol, or ICMP, echo request packets to the target host and waiting for an ICMP response. Traceroute. Traceroute is a computer network diagnostic tool for displaying the route or path and measuring transit delays of packets across an Internet Protocol or IP network. The history of the route is recorded as the round-trip times of the packets received from each successive host or remote node in the path. The sum of the mean times in each hop indicates the total time spent to establish the connection. Traceroute proceeds unless all 3 sent packets are lost more than twice. Then the connection is lost and the route cannot be evaluated. Traceroute sends a sequence of 3 Internet Control Message Protocol, or ICMP, echo request packets addressed to a destination host. Objective 4.02. Check and interpret port lockdown settings and packet filters in order to determine the cause of a management connectivity issue to a self-IP. Given a scenario, report port lockdown settings on the self-IP to determine the cause of the issue. There's a link here. Port lockdown is a big IP security feature that allows you to specify particular protocols and services from which the self-IP address defined on the big IP system can accept traffic. The port lockdown feature allows you to secure the big IP system from unwanted connection attempts by controlling the level of access to each self-IP address defined in the system. Each port lockdown list setting specifies the protocols and services from which a self-IP can accept connections. The system refuses traffic and connections made to a service or protocol port that is not on the list. Port lockdown setting definitions. Allow default. This option allows access for a predefined set of network protocols and services that are typically required in big IP deployment. The Allow Default setting specifies that connections to the self-IP addresses are allowed from the following protocols and services. And then there's a table listed here with allowed protocol, service, and service definition. You can also determine the default supported protocols and services using the following command: tmsh list net self allow. The output will appear similar to the following example: net self allow defaults OSPF any, TCP domain, TCP F5 query, TCP HTTPS, TCP SNMP, TCP SSH, UDP 520, UDP cap, UDP domain, UDP F5 iQuery, and UDP SNMP. Allow all. This option specifies that all connections to the self-IP address are allowed, regardless of protocol or service. Allow none. This option specifies that no connections are allowed on the self-IP address, regardless of protocol or service. However, ICMP traffic is always allowed, and if the big IP systems are configured in a redundant pair, ports that are listed as exceptions are always allowed from the peer system. Allow custom. This option allows you to specify the protocols and services for which connections are allowed on the self-IP address. However, ICMP traffic is always allowed, and if the big IP systems are configured in a redundant pair, ports that are listed as exceptions are always allowed from the peer system. Default port lockdown setting. When creating a self-IP address, the default port lockdown setting in big IP 10 is allow default. In big IP 11, the default port lockdown setting is none. Modifying port lockdown settings for a specific self-IP using the configuration utility. Log into the configuration utility, click Network, click Self-IPs, click the relevant self-IP address. Select the desired setting from the port lockdown box. Click Update. Modifying port lockdown settings from the TMSH utility. Log into the Traffic Management Shell, TMSH, by entering the following command. TMSH. Note, if you are currently logged into the TMSH shell, you can skip this step. To modify the port lockdown settings for a self-IP address, use the following command syntax: modify /net self and then the self-IP, allow service and then the option. For example, to change the port lockdown setting for a self-IP address 10.10.10.1 to default, you would type the following command: modify /net self 10.10.10.1 allow-service default. Save the change by typing the following command: big IP 10.1 and later, save sysconfig, big IP 10, save config. 4.02. Describe appropriate use cases for the use of a port lockdown. And there's a link here. For optimal security, F5 recommends using the port lockdown feature to allow only the protocols or services required for a self-IP address. If you are managing the big IP platform from one of the self-IP addresses rather than using the out-of-band management interface, you run the risk of users having access to the self-IP address on a port that will allow administration of the big IP platform. All external-facing self-IP addresses should be restricted to only necessary ports for the big IP platform to communicate to other necessary big IP platforms or other necessary network functions such as DNS servers, etc. Objective 4.03. Given the use of a remote authentication server, verify proper DNS and NTP settings in order to diagnose a connectivity issue. Due to the 201 exam blueprint having an obvious mistake with layout or objectives, I have modified this section's example points to reflect the objectives from the last blueprint. And there's a link here. Remote Authentication Intro. A significant feature of Big IP Local Traffic Manager is its ability to support Pluggable Authentication Module, or PAM technology. PAM technology allows you to choose from a number of different authentication and authorization schemes to use to authenticate or authorize network traffic. The goal of PAM technology is to separate an application, such as the Big IP system, from its underlying authentication technology. This means that you can dictate the particular authentication or authorization technology that you want the Big IP system to use to authenticate application traffic coming into the Big IP system. To this end, Local Traffic Manager offers several authentication schemes, known as authentication modules. These authentication modules allow you to use a remote system to authenticate or authorize application requests that pass through the Big IP system. The Big IP system normally routes remote authentication traffic through a traffic management microkernel, TMM, switch interface. That is, an interface associated with a VLAN and a self-IP address, rather than through the management interface. Therefore, if the TMM service is stopped for any reason, remote authentication is not available until the service is running again. Big IP System Authentication Modules. Local Traffic Manager authentication modules that you can implement for remote authentication are Lightweight Directory Access Protocol, or LDAP. Local Traffic Manager can authenticate or authorize network traffic using data stored on a remote LDAP server or a Microsoft Windows Active Directory server. Client credentials are based on basic HTTP authentication, username and password. Remote Authentication Dial-In User Service, or RADIUS. Local Traffic Manager can authenticate network traffic using data stored on a remote RADIUS server. Client credentials are based on basic HTTP authentication, username and password. TACACS Plus. Local Traffic Manager can authenticate network traffic using data stored on a remote TACACS Plus server. Client credentials are based on basic HTTP authentication, username and password. SSL Client Certificate LDAP. Local Traffic Manager can authorize network traffic using data stored on a remote LDAP server. Client credentials are based on SSL certificates as well as defined user groups and roles. Online Certificate Status Protocol, OCSP. Local Traffic Manager can check on the revocation status of a client certificate using data stored on a remote OCSP server. Client credentials are based on SSL certificates. Certificate Revocation List Distribution Point, CRLDP. Local Traffic Manager can use CRL distribution points to determine revocation status. Kerberos Delegation. Local Traffic Manager can authenticate application traffic when you are using Microsoft Windows Integrated Authentication. Given a suspected DNS issue, use appropriate tools to verify proper settings. GUI study in the VLabs, and there is a link here. For the Big IP platform to connect to a node by name or to get to any system for any reason by the server's DNS name, a DNS server must be configured on Big IP settings. The Big IP system uses two sources of information to resolve host names, the host file and DNS. The Big IP system first refers to the local etc hosts file. If the host name is not found in the etc hosts file, the Big IP system uses DNS if configured to do so. The following procedures help you configure the Big IP system to use DNS. Using the Big IP configuration utility is the preferred method of configuring a DNS remote lookup server. Impact of procedure. Performing the following procedures should not have a negative impact on your system. Log into the Big IP system configuration utility. Click System, click Configuration, click Device, click DNS. In the DNS Lookup Server List section, type the IP address of your remote DNS lookup server. Click Add. Complete the change by clicking Update. The same procedure can be used to modify the bind forwarder service list on DNS search domain list. If this setting is not configured, then resolving a DNS name from the Big IP platform will fail, including resolving the name of the remote authentication server for remote authentication. Given a suspected DNS issue, use appropriate tools to verify DNS response. GUI study in the VLabs. If the DNS issue is related to the Big IP platform connecting to a DNS name, you can check to make sure that the system is able to resolve names. From the command prompt, you can do an NS lookup of a server name, or you can dig the server name. Both of these tools are found on the BigIP platform. NSLookup example. NSLookup www.stonygrayband.com. Server 192.168.691. Address 192.168.69.1 #53. Non-authoritative answer www.stonygrayband.com. Canonical name equals stonygrayband.com. Name stonygrayband.com. Address 71.251.96.82. A dig example. Dig www.stonygrayband.com. And then it gives you the response you would get from a dig. Section 5. Open a support ticket with F5. Objective 5.01. Identify the appropriate supporting components and severity levels for an F5 support ticket. Identify the necessary components for all support cases. Quick view uploaded to iHealth or attached to case, serial number of device, problem description, other supporting data. There's a link here. F5 technical support can help resolve issues more quickly when you provide a full description of the issue and the details of your configuration. To help you gather all the required information, use the following guidelines to prepare for opening a case. General information. Provide the following information when you open a case with F5 technical support. 1. A full description of the issue, including the following details: the symptoms of the issue, the approximate time the issue first occurred, the number of times the issue has recurred, any error output provided by the system, steps to reproduce the issue, any changes you made to the system before the issue first occurred, and any steps you have attempted to resolve the issue. 2. A description of the impact of the issue is having on your site using the following definitions. Site down, which is all network traffic has ceased, causing a critical impact to your business. Site at risk, primary unit has failed, resulting in no redundancy, site is at risk of going down. Or performance degraded, network traffic is partially functional, causing some applications to be unreachable. 3. The hours that you are available to work on the issue and any alternative contacts that can work on the issue if you are not available. 4. Remote access information if possible. Remote access to your network environment is important because it is the most effective method for collecting information and troubleshooting technical issues. If you cannot provide remote access, F5 technical support will work directly with you to resolve the issue over the phone. However, this method can often be more time-consuming and may require file transfers, replication, and additional testing. Collect the following information from the affected systems and provide the information when you open the case: a quick view or tech.out file. The quick view utility is a BigIP program that an administrator can use to automatically collect configuration and diagnostic information from a BigIP Enterprise Manager systems. Starting in BigIP 10.0.0, the Quick View utility is an executable program that generates machine-readable XML diagnostic data from the BigIP or Enterprise Manager system and combines the data into a single compressed tar file. The diagnostic file can then be uploaded to the BigIP iHealth or given to F5 technical support to aid in troubleshooting. Note, if you are running BigIP version 10x or later, you can use BigIP iHealth to diagnose a quick view file. BigIP iHealth diagnoses the health and proper operation of your BigIP system when you upload the quick view file to the BigIP iHealth website. For more information, refer to the BigIP iHealth website. Log files. Note, the quick view utility automatically gathers 5 MB of log files and includes them with quick view in a .tar output. If the system's logs are heavy and more of the logs are needed, provide all the log files on the system by performing the following procedures. Log in to the command line, create a tar archive named logfiles.tar.gz in the var temp directory, which contains all the files in the var log directory, by typing the following command. And then it lists the command, which you should look up. Packet traces. If the issue involves the network, perform a packet trace while the issue is occurring and provide the packet trace when you open the case. Note, for more information about performing packet traces with TCP dump, refer to SOL 4714, performing a packet trace and providing the results to F5 technical support. UCS archive. If you cannot give F5 technical support remote access to your system, you may need to provide a UCS archive of the current configuration. For more information, refer to SOL 4423, Overview of UCS Archives. Core files. Core files contain the contents of the system memory at the time a crash occurred. If the system has been configured to save core files, they will be located in the var save core directory, BIG-IP versions 9 through 9.25, or var core directory for BIG-IP versions 9.3 and later. Provide any existing core files when you open the case. Note, for information about requirements when submitting core files to F5, refer to SOL 10062, Submitting Core Files for Analysis to F5 Technical Support. Identify severity levels and the associated response times. And there's a link here. All F5 network support centers uphold the following case severity definitions and target response times to ensure that the appropriate resources are used to resolve all technical issues as efficiently as possible. F5 will endeavor to respond to Severity 1 and Severity 2 issues within 1 hour, understanding that unforeseen events could delay attempts. F5 expects that the majority of Severity 1 and Severity 2 issues will be responded to within this service level. Initial response is defined as the time from when the F5 case was created to when a network support engineer first attempts to contact the case contact for troubleshooting and updates the case log reflecting this action. Severity 1. 1 hour response. Software or hardware conditions on your F5 device are preventing the execution of critical business activities. The device will not power up or is not passing traffic. Severity 2, 1 hour response. Software or hardware conditions on your F5 device are preventing or significantly impairing high-level commerce or business activities. Severity 3, 4 business hour response. Software or hardware conditions on your F5 device are creating degradation of service or functionality in normal business or commerce activities. Severity 4, 24-hour response. Questions regarding configurations, i.e. how-to, troubleshooting non-critical issues, or requests for product functionality that is not part of the current product feature set. When a case is logged as Severity 1, F5 network support managers are immediately notified to ensure the case is assigned within the appropriate timeframe to an appropriately skilled network support engineer. Objective 5.02. Given an issue, determine the appropriate severity according to F5 guidelines, and there's a link. Severity 1. Software or hardware conditions on your F5 device are preventing the execution of critical business activities. The device will not power up or is not passing traffic. Severity 2. Software or hardware conditions on your F5 device are preventing or significantly impairing high-level commerce or business activities. Severity 3. Software or hardware conditions on your F5 device are creating degradation of service or functionality in normal business or commerce activities. Severity 4. Questions regarding configurations or how-tos, troubleshooting non-critical issues, or requests for product functionality that is not part of the current product feature set. Objective 5.03. Provide quantitative and relevant information appropriate for a given issue. Distinguish between qualitative and quantitative statements in order to assemble an accurate problem description. General network study. This blueprint topic is related to choosing the correct answer for a scenario type question. Hands-on study is the best way to master these topics. Quantitative observations are observations that can be precisely measured. For example, there is taking an additional 20 seconds per connection over the connection times this morning. Qualitative observations have more to do with characteristics of what is being observed, i.e., it seems to be taking longer to connect than it did this morning. Distinguish between relevant and irrelevant information in order to assemble an accurate problem description. General network study. Again, hands-on is the best way. Is the information that you are gathering relative to the issue you are experiencing? Troubleshooting can lead to many rat holes where you can get lost from the real issues. Make sure you're providing the right info. Section 6. Identify and report current device status. Objective 6.01. Review the network map in order to determine the status of objects. Explain the status icons of objects on the map. And there's a link. The configuration utility includes a feature known as the network map. The network map shows a summary of local traffic objects as well as a visual map of the virtual servers, pools, and pool members on the BIG-IP system. For both the local traffic summary and the network map, you can customize the display using a search mechanism that filters the information that you want to display, according to criteria that you specify. the system highlights in blue all matches from a search operation. Object Summary. When you first open the network map screen, the screen displays a summary of local traffic objects. This summary includes the type of objects specified with the search mechanism, the number of each type of object, and for each object type, the number of objects in a given status. The summary displays data for these object types: virtual servers, pools, pool members, nodes, iRules. Note: a local traffic summary includes only those objects that are referenced by a virtual server. For example, if you have configured a pool on the system but there is no virtual server that references that pool, the local traffic summary does not include that pool, its members, or the associated nodes in the summary. The diagram below shows an example of a network map screen that summarizes local traffic objects on the system. And then there's a screenshot. For each object type listed in the summary, the system shows the number of objects with each type of status. Table 1.3 shows the various status indicators that the summary screen can display for a local traffic object. And then there is a table here. The status indicator, if it is green circle, the objects are enabled and available or able to receive traffic. If it is a yellow triangle, the objects are enabled but are currently unavailable. However, the objects might become available later with no user action required. An example of an object showing this status is a virtual server whose connection limit has been exceeded. When the number of connections falls below the configured limit, the virtual server becomes available again. A red diamond. The objects are enabled but offline because an associated object has marked the object as unavailable. To change the status so that the object can receive traffic, you must actively enable the object. A blue square. The status of the object is unknown. The network map presents a visual hierarchy of the names and status of virtual servers, pools, pool members, nodes, and iRules defined on the system. The map shows all objects in context, starting with the virtual servers at the top. The status, type, and search settings at the top of the screen determine the objects that the map includes. When you position the cursor over an object on the map, the system presents hover text containing information about the object. When you position the cursor over the status icon accompanying an object, the system presents hover text containing information about the object's status, text which also appears on the pool's properties screen. The system arranges objects in alphabetic order and organizes the dependent objects in a hierarchy. Due to the way that the network map presents objects in context, the updated screen also shows objects of other statuses, types, and names that relate to those objects. This is because a network map always shows objects in context with the objects that depend on them and the objects they depend on. For example, if you have an available virtual server with an available pool and two pool members, one available and one offline, then selecting offline from the status list causes the system to show the offline pool member in the context, with the available virtual server and the available pool. This is because the available virtual server and the available pool depend on the offline pool member. And there's a screenshot here. Explain what virtual servers, pools, and nodes and pool members are. And there's a screenshot here. Virtual server. A virtual server is a traffic management object on the Big IP system that is represented by an IP address and a service. Clients on an external network can send application traffic to a virtual server, which then directs the traffic according to your configuration instructions. The main purpose of a virtual server is often to balance traffic load across a pool of servers on an internal network. Virtual servers increase the availability of resources for processing client requests. Not only do virtual servers distribute traffic across multiple servers, they also treat varying types of traffic differently, depending on your traffic management needs. For example, a virtual server can enable compression on HTTP request data as it passes through the Big IP system, or decrypt and re-encrypt SSL connections and verify SSL certificates. For each type of traffic, such as TCP, UDP, HTTP, SSL, SIP, and FTP, a virtual server can apply an entire group of settings to affect the way that local traffic manager manages that traffic type. A virtual server can also enable session persistence for a specific traffic type. Through a virtual server, you can set up session persistence for HTTP, SSL, SIP, and MSRDP sessions, to name a few. Finally, a virtual server can apply an iRule, which is a user-written script designed to inspect and direct individual connections in specific ways. For example, you can create an iRule that searches the content of a TCP connection for a specific string and, if found, directs the virtual server to send the connection to a specific pool or pool member. To summarize, a virtual server can do the following: distribute client requests across multiple servers to balance server load, apply various behavioral settings to a specific type of traffic, enable persistence for a specific type of traffic, direct traffic according to user-written iRules. And then there's a link here. Pool and pool members. A load balancing pool is a logical set of devices such as web servers that you group together to receive and process traffic. Instead of sending client traffic to the destination IP address specified in the client request, Local Traffic Manager sends the request to any of the servers that are members of that pool. This helps to efficiently distribute the load on your server resources. When you create a pool, you assign pool members to the pool. A pool member is a logical object that represents a physical node or server on the network. You then associate the pool with a virtual server on the Big IP system. Once you have assigned a pool to a virtual server, Local Traffic Manager directs traffic coming into the virtual server to a member of that pool. An individual pool member can belong to one or multiple pools, depending on how you want to manage your network traffic. The specific pool member that the Local Traffic Manager chooses to send the request to is determined by the load balancing method that you have assigned to the pool. A load balancing method is an algorithm that Local Traffic Manager uses to select a pool member for processing a request. For example, the default load balancing method is round robin, which causes Local Traffic Manager to send each incoming request to the next available member of the pool, thereby distributing requests evenly across the servers in the pool. To configure and manage pools, log into the Big IP configuration utility, and on the main tab, expand Local Traffic and click Pools. There's a link. Nodes. A node is a logical object on the Big IP Local Traffic Manager system that identifies the IP address of a physical resource on the network. You can explicitly create a node, or you can instruct Local Traffic Manager to automatically create one when you add a pool member to a load balancing pool. The difference between a node and a pool member is that a node is designated by the device IP address only, for example 10.10.10.10, while designation of a pool member includes an IP address and a service, such as 10.10.10.10.80. A primary feature of nodes is their association with health monitors. Like pool members, nodes can be associated with health monitors as a way of determining server status. However, a health monitor for a pool member reports the status of a service running on the device, whereas a health monitor associated with the node reports status of the device itself. For example, an ICMP health monitor is associated with node 10.10.10.10, which corresponds to pool member 10.10.10.10:80, and the monitor reports the node as being in a down state. Then the monitor also reports the pool member as being down. Conversely, if the monitor reports the node as being in an up state, then the monitor reports the pool member as being either up or down, depending on the status of the service running on it. Nodes are the basis for creating a load balanced pool. For any server that you want to be part of a load balancing pool, you must first create a node. That is, designate that server as a node. After designating the server as a node, you can add the node to a pool as a pool member. You can also associate a health monitor with the node to report the status of that server. To configure and manage nodes, log into the Big IP configuration utility, and on the main tab, expand local traffic and click Nodes. Objective 6.02. Use the dashboard to gauge the current running status of the system. Interpret each of the statistic types displayed by the dashboard. GUI study in the VLabs. The main dashboard screen is of the system overview. This screen displays a graphical representation of CPU utilization, memory utilization, connections, and throughput of the system. And there's a screenshot. Given a situation, predict the appropriate dashboard statistics. GUI study in the VLabs. Understand what situations and which configurations will affect the different areas of the dashboard statistics. For example, the more features that are provisioned on the Big IP platform, the higher the base memory utilization will be. Also, if ASM is running on the Big IP, the CPU utilization may get higher as additional policies are added to the configuration under load. Objective 6.03. Review log files and identify possible events. Given log file snippets, describe an event sequence. GUI study in the VLabs. This blueprint topic is related to choosing the correct answer for a scenario. It's best to use hands-on study to master these topics. So get familiar with looking at the event logs on the Big IP and learn to reconstruct what has happened recently based on the events in the logs. Given log file snippets, identify critical events. And again, this is best done with hands-on study. And so get familiar with looking at the event logs on the Big IP and be able to identify the critical events. This may be hard to do in the lab unless you are creating your own system errors. If possible, do the opposite and get used to seeing what is there when all is good, and then the errors will stand out. Objective 6.04. Use iApps Analytics to gauge the current running status of application services. Explain the purpose of iApps Analytics, and there is a link here to reference. What is analytics? Analytics, also called application visibility and reporting, is a module on the Big IP system that lets you analyze performance of web applications. It provides detailed metrics such as transactions per second, server and client latency, request and response throughput, and sessions. You can view metrics for applications, virtual servers, pool members, URLs, specific countries, and additional detailed statistics about application traffic running through the Big IP system. Transaction counters for response codes, user agents, HTTP methods, countries, and IP addresses provide statistical analysis of the traffic that is going through the system. You can capture traffic for examination and have the system send alerts so you can troubleshoot problems and immediately react to sudden changes. The Analytics module also provides remote logging capabilities so that if your company can consolidate statistics gathered from multiple Big IP appliances onto syslog servers or SIEM devices such as Splunk. About analytics profiles. An analytics profile is a set of definitions that determines the circumstances under which the system gathers, logs, notifies, and graphically displays information regarding traffic to an application. The Analytics module requires that you select an analytics profile for each application you want to monitor. You associate analytics profile with one or more virtual servers used by the application or with an iApps application service. Each virtual server can have only one analytics profile associated with it. In the analytics profile, you customize what statistics to collect, where to collect data, locally, remotely, or both, where to capture the traffic itself, and whether to send notifications. The Big IP system includes a default analytics profile called Analytics. It is a minimal profile that internally logs application statistics for server latency, throughput, response codes, and methods. You can create custom analytics profiles for each application if you want to track different data for each one. Charts shown in the Overview Statistics Analytics screen display the application data saved for all analytics profiles associated with iApps application services or virtual servers on the system. You can filter the information, for example, by application or URL. You can also drill down into the specifics on the charts and click the tabs to further refine the information in the charts. Describe how to capture application statistics, and there is a link. You can examine the statistics on the analytics charts when application visibility and reporting, AVR, is provisioned. The system recalculates the analytics statistics and updates the charts every 5 minutes. Before you can look at the application statistics, you need to have created an analytics profile so that the system is capturing the application statistics internally on the Big IP system. You must associate the analytics profile with one or more virtual servers in the analytics profile or on the virtual server. If you created an iApp application service, the template provided allows you to associate to the virtual server. To view analytics statistics properly, Adobe Flash Player must be installed on the computer where you plan to view them. The task summary of how to set up the Big IP system to collect application performance statistics can be found in the Setting Up Local Application Statistics Collection section of the hyperlinked site. The system can collect application statistics locally, remotely, or both. You use these statistics for troubleshooting and improving application performance. You can collect application statistics for one or more virtual servers or for an iApps application service. If virtual servers are already configured, you can specify them when setting up a statistics collection. If you want to collect statistics for an iApps application service, you should first set up statistics collection, creating an analytics profile, and then create the application service. The system can send alerts regarding the statistics when thresholds are exceeded and when they cross back into the normal range. You can customize the threshold values for transactions per second, latency, page load time, and throughput. Given a current running status, recognize significant statistics. GUI study in the VLabs. This topic is related to choosing the correct answer for a scenario type question, so it's best to do hands-on study. Get familiar with looking at the status information in Statistics, Module Statistics, Local Traffic, under the different statistics types drop menu on the Big IP, and be able to identify significant statistics levels. This may be hard to do in the lab unless you are pushing load through the unit. Get used to how the reports look and how to read them. Section 7. Maintain System Configuration. Objective 7.01. Create and restore a UCS archive under the appropriate circumstances. Discuss scenarios in which restoring a UCS archive is appropriate. There's a link here. Once you have created the configuration data for the Big IP system, you can replicate all of this set of data in a separate file. You can then use this replicated data later for these reasons, as an archive for disaster recovery, or using the archives feature, you can back up the current configuration data and, if necessary, restore that data at a later time. We highly recommend that you use this feature to mitigate the potential loss of Big IP system configuration data. To create an archive, you can use the configuration utility, which stores the configuration data in a special file known as a user configuration set, or UCS file. You can then use the UCS file to recover from any loss of data in the unlikely event that you need to do so. Discuss the tasks involved in successfully restoring a UCS archive. And there's a link here as well. There are a few different ways to do a UCS restore on a Big IP system. Restoring configuration data by using the configuration utility. Impact of procedure. The Big IP system replaces any existing configuration with the UCS archive file configuration. If you are restoring a UCS archive on a Big IP 6400, 6800, 8400, or 8800 hardware platform other than the system from which the backup was created, such as when replacing an RMA system, you must perform the procedure in the restoring configuration data from the command line by using the TMOS utility section of this article to restore the configuration. To restore a configuration in a UCS archive by using the configuration utility, review the considerations described in the Considerations for Restoring Configuration Data section of this article before performing the following procedure. 1. Log into the configuration utility. 2. Click System. 3. Click Archives. 4. Click the name of the UCS archive you want to restore. 5. If the UCS archive is encrypted, type the passphrase for the encrypted UCS archive file in the Restore Passphrase field. If the UCS archive is not encrypted, you can skip this step. To initiate the UCS archive restore process, click Restore. When the restore process is completed, examine the status page for any reported errors before proceeding to the next step. And then last step, number 8, return to the archive list page and click OK. If you restored the UCS archive on a different device and received the errors noted in the Consideration for Restoring Configuration Data section of this article, you must reactivate the Big IP system license. After relicensing the system, restart the system to ensure that the configuration is fully loaded. To restart the system, navigate to System, Configuration, and then click Reboot. If the system you restored contains the FIPS 140 HSM, you must configure the FIPS 140 HSM security world after completing steps 1 through 9. For additional information about recovering FIPS information after a system recovery, refer to the Configuring and Maintaining a FIPS Security Domain chapter in the Platform Guide 6900 and 8900. Restoring configuration data from the command line by using the TMOS utility. Impact of procedure. The Big IP system replaces any existing configuration with the UCS archive file configuration. Log in to TMOS by typing the following command. TMOS. Restore the UCS archive file by using the following command syntax. Replace path to UCS with the full path of the UCS archive you want to restore. Load /sys UCS and then path to UCS. If you do not specify the path, the Big IP system performs as if the UCS archive file is located in the default var local UCS directory. 3. If the UCS archive file was encrypted with a passphrase during the backup, you are prompted to enter the passphrase for the archive file. 4. If you are running Big IP on a 6400, 6800, 8400, or 8800 hardware platform, type the following command to switch to the bash shell. run/util bash. Type the following command to verify that the new or replaced secure shell or SSH keys from the UCS file are synchronized between the big IP system and the switch card control processor or SCCP, keyswap.sh SCCP. 6. Type the following command to switch back to TMSH. Exit. 7. Restart the system by typing the following command. Reboot. 8. If you installed the UCS archive on the same device on which the backup was created, it loads the restored configuration after the system restarts. If you restored the backup on a different device and received the first error noted in the considerations for restoring configuration data section of this article, you must reactivate the big IP system license. Alternatively, you can replace the config bigip.license file with the original bigip.license file that you backed up from the target system. If the system you restored contains FIPS 140 HSM, you must configure the FIPS 140 HSM security world after completing steps 1 through 5. For additional information about recovering FIPS information after a system recovery, refer to the Configuring and Maintaining a FIPS Security Domain chapter in the Platform Guide 6900 and 8900. Restoring configuration data on a replacement RMA unit. F5 recommends that you use the following procedure when you restore the archive on a different device than the system on which the backup was created, such as an RMA system. If you do not use this procedure when restoring the archive on a different device, the configuration load may fail and the MCPD process generates an error message that appears similar to the following example to both stdout and the var log LTM file. Basically says license is not operational, expired or digital signature does not match contents. F5 expects this message and you can correct the issue by relicensing the system, which is discussed later in the procedure. Impact of procedure. The big IP system replaces any existing configuration with the UCS archive file configuration. 1. Activate the license on the unit according to the steps detailed in SOL 7752, Overview of Licensing the Big IP System. 2. Log into TMSH by typing the following command, TMSH. 3. Restore the UCS archive file by using the following command syntax. Replace path to UCS with the full path of the UCS archive file you want to restore. For example, load/UCS, path to UCS, no-license. If you do not specify the path, the big IP system performs as if the UCS archive is located in the default var local UCS directory. 4. If the UCS archive file was encrypted with a passphrase during the backup, you are prompted to enter the passphrase for the archive file. 5. If you are running big IP system on a 6400, 6800, 8400, or 8800 hardware platform, switch to the bash utility by entering the following command, run/util bash. 6. To verify that the new or replaced SSH keys from the UCS file are synchronized between the big IP and the SCCP, enter the following command, keyswap.sh SCCP. 7. To exit back to TMSH, type the following command, exit. 8. Restart the system by typing the following command, reboot. 9. If the system you restored contains the FIPS 140 HSM, you must configure the FIPS 140 HSM security world after completing steps 1 through 5. For additional information about recovering FIPS information after a system recovery, refer to the Configuring and Maintaining a FIPS Security Domain chapter in the Platform Guide 6900 and 8900. Restoring UCS archives on big IP systems running later software versions. Impact of procedure. The big IP system replaces any existing configuration with the UCS archive file configuration. F5 recommends that the big IP system run the same version of the big IP software from which it was backed up. However, in some cases, it is possible to restore a UCS archive that was obtained from an earlier software version on a target big IP system running a later software version. For example, if you saved a UCS archive on a system running big IP 10.2.3, it is possible to restore the version big IP 10.2.3 archive file on a big IP system running 11x. To restore a UCS archive on a big IP system running a later software version, perform the following procedures. 1. Verify that a supported upgrade path exists between the software version from which the UCS archive was obtained and the software version running on the target system. For example, there is a supported upgrade path between big IP 10x and big IP 11x. As a result, you can successfully restore a Big IP 10x UCS archive file on a Big IP system running 11x. However, there is no supported upgrade path between a Big IP 9x and Big IP 11x. As a result, you cannot restore Big IP 9x UCS archive on a Big IP system running 11x. For information about supported upgrade paths, refer to the product release notes for your specific software version. 2. Review the previous section, Considerations for Restoring Configuration Data. 3. Manually copy the UCS archive file to the var local UCS directory on the target system. 4. Restore the UCS archive on the Big IP system. If you are restoring the archive on a different device than the system on which the backup was created, follow the Restoring Configuration Data on a Replacement RMA Unit procedure. If you are restoring the archive on a different device than the system on which the backup was created, follow the Restoring Configuration Data from the command line by using the TMSH utility procedure. Given a scenario, discuss when it is appropriate to create a UCS archive. GUI study in the VLabs. Anytime the system administrator makes changes to the configuration of the system, a UCS archive should be taken prior to the change and after the change. This will allow a restore to the point prior to the change and also provides a backup to the new current state. This should be done on both the active and standby systems in an HA pair. Objective 7.02. Identify which high-level tasks can be automated using BigIQ. Identify which high-level tasks can be automated using BigIQ, and there's a link here. BigIQ Application Delivery Controller, ADC, makes it possible for you to monitor and manage the Local Traffic Manager, or LTM, configuration on BigIP devices. This module helps the user create efficient workflows to view the LTM configurations in a relational and dynamic user interface, control access to configuration objects using fine-grained role-based access control, RBAC. This allows administrators to delegate frequently performed operations, for example, enabling or disabling pool members, to the correct team member. Maintain ultimate control of the LTM configuration by providing a staging option. Delegated team members make all relevant changes, then the administrator can apply them after a quick review. BigIQ ADC has two primary interfaces, configuration and deployment. Use the configuration interface to work with the settings for the devices the BigIQ device manages. The configuration interface has two interactive modes, on BigIQ and on BigIP. When BigIP is selected, the settings that display for the managed devices are from the most recent sync. You cannot make changes to these settings when BigIP is selected. When on BigIQ is selected, the settings that display for the managed devices still include the most recent sync settings, but also include any revisions you have made. Use the deployment interface to apply configuration changes that were made on the BigIQ device to the managed devices. To get familiar with BigIQ for the exam, you should download the VE of BigIQ and set it up in your VLab environment. Objective 7.03, Managing Software Images, and there's a link. The BigIP system allows you to install and delete additional software images on separate boot locations, also called volumes. You can then boot the BigIP system to a specific volume and begin processing traffic using that specific software version. By default, the BigIP system has 3 volumes that appear similar to the following example. And then it shows the 3 typical BigIP volumes. You can find step-by-step instructions on loading software onto the BigIP in this section's hyperlink. Potential impact of booting devices into another volume. Booting the BigIP platform into another volume may put the system in an inaccessible state if the circumstances are right. Just because there is an OS loaded onto a volume does not mean that there is any configuration other than the default configuration on the volume. The out-of-band management may still be set to the default IP address, and you could lose your management connection to the unit. Or, if this was a volume that was used in the past, it will likely be in the state it was in when the system was booted into another volume. This could mean that it is running some older configuration that is not the same as the current configuration in the current volume. Or the system could even be licensed differently, leaving some functions of the OS not even enabled. The cpcfg command allows you to copy a configuration from a specified source boot location to a specified target boot location. If the specified target boot location is an earlier version than the source boot location, the command fails with an error message. If the specified target boot location is the active boot location, the command fails with an error message. Common issues related to the migration of a device to a new software version, and there's a link here. If the device you are migrating to a new software version is not an HA pair, the upgrade will cause an outage, so plan accordingly. When dealing with an HA pair of devices, upgrades should be done on the units in the standby state to minimize outages. A hotfix to an existing software version is normally non-impactful to the operation of the unit. However, it is still a best practice to upgrade the standby unit first, confirm the upgrade, fail over the pair, and proceed with upgrading the now standby unit. Always follow the F5 solution or the SOLs for installing the software. Some common issues that can be impactful to an environment when doing software upgrades are known issues with the release, iRule compatibility with the newer version, and older version configurations migrating forward successfully. Before upgrading to the next desired version of OS, the administrator should read all the release notes to make sure that the known issues on that release will not impact with the configurations currently running. iRules are compiled scripts running on the system's current version of code. Changes in the OS can change how the iRule functions, or functions at all, between versions. Testing the OS upgrade in a lab environment is the best way to make sure that there is no failing iRules after an upgrade. Also, reading through the Dev Central reference on commands and events by version is a good place to start, and there's a link. When migrating from older releases to a newer major release of OS, there can be issues with configuration migration to the newer release. You should always read the release notes and follow the recommended migration path for the version on the Ask F5 site. Objective 7.04. Given an HA pair, describe the appropriate strategy for deploying a new software image. Given an HA pair, describe the appropriate strategy for deploying a new software image. And there is a link. The upgrade process involves preparation of the two big IP devices, device A and device B, configured in an active standby implementation, followed by the installation and verification of version 11 on each device. When you upgrade each device, you perform several tasks. Completing these tasks results in successful upgrade to version 11 on both big IP devices, with the traffic group configured properly for an active standby implementation. On a properly configured HA pair of big IP devices, a software upgrade should always be done on the standby unit in the pair. This allows the upgrade to be hitless to the extent of nothing greater than a failover between functioning units in the HA pair. Objective 7.05. Understand the processes of licensing, license reactivation, and license modification or add-ons. There's a link here. Before you can configure and use the big IP system, you must activate a valid license on the system. To license the big IP system, you must perform the following procedures: obtain a registration key, obtain a dossier, activating the license. Obtaining a registration key. Before you can activate the license for the big IP system, you must obtain a base registration key. The base registration key is a 27-character string that instructs the license server which F5 products you can license. The base registration key is pre-installed on new big IP systems. When you connect to the configuration utility, the licensing screen opens and displays the registration key. Obtaining a dossier. The dossier is an encrypted list of key characteristics used to identify the platform, which you can obtain from the big IP software. The dossier is generated by your F5 product after you choose a license activation method. Activating the license. If your big IP system is not yet licensed and you connect to the configuration utility, you are prompted to enter the base registration key. Certain systems may require you to enter keys for additional modules in the add-on registration key list box. To activate the license on the big IP system using the configuration utility, you can use either the automatic activation method or the manual activation method. The activation method specifies the method by which you want the system to communicate with the F5 license server. The license activation date is unique to the device that the dossier is derived from. For step-by-step procedures, please review the content via the hyperlink. Objective 7.06. Identify which modules are licensed and/or provisioned. There's a link here. Using the configuration utility, you can easily display the licensed software and see which of the software modules are provisioned to run on the platform. Simply go to System, Resource Provisioning, and see the current configuration. And there's a screenshot here. Objective 7.07. Explain how to create a user. There's a link. An important part of managing the big IP system is creating and managing user accounts for big IP system administrators. By creating user accounts for system administrators, you provide additional layers of security. User accounts ensure that the system verifies the identity of users logging into the system, authentication, controls user access to system resources, authorization. To enable user authentication and authorization, you assign passwords and user roles to your user accounts. Passwords allow you to authenticate your users when they attempt to log into the Big IP system. User roles allow you to control user access to Big IP system resources. You can create and store Big IP administrative accounts either locally on the Big IP system or remotely on a separate authentication server. If you want your user accounts to reside locally on the Big IP system, you can create those user accounts on the Big IP system and assign user roles to them. If you want your user accounts to reside remotely on a separate authentication server, you do not use the Big IP system to create accounts. Instead, use the mechanism provided by the server vendor, and you use the Big IP system strictly to assign user roles to those remote accounts and to maintain those user role assignments over time. The types of servers that you can use to remotely store Big IP system user accounts are Lightweight Directory Access Protocol or LDAP servers, Active Directory servers, Remote Authentication Dial-In User Service, or RADIUS servers. User account types. There are two types of user accounts in the Big IP system, the System Maintenance Account and a set of standard user accounts. The System Maintenance Account is a user account that you maintain using the setup utility. The name of the System Maintenance Account is root. This account resides locally on the Big IP system and grants full access to Big IP system resources. You configure and maintain this account using the setup utility and the configuration utility respectively. Standard user accounts. Standard user accounts are user accounts that you create for other Big IP system administrators to use. Standard user accounts can reside either locally on the Big IP system or remotely on a remote authentication server. You create and maintain these accounts using the browser-based configuration utility or the command line interface. Creating standard user accounts allows you to assign various user roles to those accounts as a way to control system administrator access to Big IP system resources. A special standard user account is the admin account, which automatically exists on any Big IP system. You are not required to have any user accounts other than the root and admin accounts, but F5 Networks recommends that you create other user accounts as a way to intelligently control administrator access to system resources. Administrative partitions. When you create configurable objects for the Big IP system, you have the option of putting those objects into administrative partitions. An administrative partition is a logical container of Big IP system objects such as virtual servers, pools, and monitors. When you first install the Big IP system, a default partition already exists named Common. By putting objects into partitions, you establish a finer granularity of access control rather than having control over all resources on the Big IP system or no resources whatsoever. Users with certain permissions can control resources within a designated partition only. For example, users with the role of operator can mark nodes up or down, but can only mark those nodes that reside within their designated partition. User accounts are another type of object that you can put into a partition. You put user accounts into administrative partitions strictly for the purpose of giving other users administrative access to those accounts. For example, you can put user accounts into partition B and then assign a set of permissions, known as a user role, to user Jane so that she is allowed to modify user accounts in partition B. Each user account on the Big IP system has a property known as partition access. The partition access property defines the partitions that the user can access. A user account can have access to either one partition or all partitions. Access to all partitions is known as universal access. The figure shows how partition access can differ for different user accounts on the Big IP system, and there's a diagram here. In this example, the Big IP system resides in multiple partitions. Note that user accounts are also a type of Big IP system object, and as such reside in a partition named users. Although you are not required to group user accounts together in a separate partition, for security purposes, F5 Networks highly recommends that you do so. To continue with the example, each user account in partition users has access to specific but different partitions. Note that user accounts S. Jones, C. Johnson, and G. Nelson can access one partition only, while the T. Brown account has universal access. To summarize, an administrative partition defines a set of objects, including user accounts, that other administrative users can potentially manage. This gives computing organizations greater control over user access to specific objects on the Big IP system. What are user roles? User roles are a means of controlling user access to big IP system resources. You can assign a user role to each administrative user, and in doing so, you grant the user a set of permissions for accessing big IP system resources. The big IP system offers several different user roles that you can choose from when assigning a role to an administrative user. A user role is a property of a user account. Each user role grants a different set of permissions. More specifically, a user role defines the resource that a user can manage. User roles define the types of resources or objects that a user can manage. For example, a user with the role of operator can enable or disable nodes and pool members only. By contrast, a user with the guest role cannot manage any big IP system resources. The tasks that a user can perform. For example, a user with the role of operator can enable or disable nodes and pool members but cannot create, modify, or delete them. Conversely, a user with the manager role can perform all tasks related to partitioned objects except for user accounts, including nodes and pool members. Important. A role defines the type of objects that a user can manage and the tasks that a user can perform on those object types. A role does not define the set of specific existing objects that the user can access. User roles on the big IP system. Administrator. This role grants users complete access to all partitions and non-partitioned objects on the system. In addition, accounts with the administrator role can change their own passwords. Resource Administrator. This role grants users complete access to all partitioned and non-partitioned objects on the system, except user account objects. In addition, accounts with the Resource Administrator role can change their own passwords. User Manager. Users with the User Manager role that have access to all partitions can create, modify, delete, and view all user accounts except those that are assigned the Administrator role or the User Manager role with different partition access. Accounts with the User Manager role that have access to all partitions can also change their own passwords. Users with the User Manager role that have access only to a single partition can create, modify, delete, and view only those user accounts that are in the partition and that have access to that partition only. For example, if your user account has a User Manager role and has access to partition A only, then you can manage only those accounts that both reside in and have access to partition A only. User accounts with the User Manager role can change their own passwords. Manager. This role grants user permissions to create, modify, and delete virtual servers, pools and members, nodes, custom profiles, and custom monitors, and iRoles. These users can view all objects on the system and change their own passwords. Certificate Manager. This role grants users permissions to manage device certificates and keys, as well as perform Federal Information Processing Standard (FIPS) operations. iRole Manager. This role grants users permissions to create, modify, and delete iRoles. Users with this role cannot affect the way that an iRole is deployed. For example, a user with this role can create an iRole but cannot assign it to a virtual server or move the iRole from one virtual server to another. A user with this role can be assigned universal access to administrative partitions. Application Editor. This role grants users permissions to modify nodes, pools, pool members, and monitors. These users can view all objects on the system and change their own passwords. Acceleration Policy Editor. This role allows users to view, create, modify, and delete all Web Accelerator policy objects in an administrative partitions. Users can also view, create, update, and delete Web Acceleration profiles. Application Security Administrator. This role grants a user access to all Application Security Manager security policy objects and the big IP system. These users have read-only permission for these profile types: HTTP, FTP, and SMTP. These users have no access for other LTM objects or any TMOS objects. They can, however, change their own passwords. With respect to security policy objects, this role is similar to the administrator role. You can assign this role only when the big IP system includes the big IP Application Security Manager component. Web Application Security Editor. This role allows a user to configure or view most parts of the Application Security Manager component in a specified administrative partition only. Specifically, these users have limited access to LTM objects, namely read-only permission to these profile types: HTTP, FTP, and SMTP. These users have no access to other LTM objects, nor to any TMOS objects. They can, however, change their own passwords. You can assign this role only when the big IP system includes the Application Security Manager component. Operator. This role grants users permissions to enable or disable nodes and pool members. These users can view all objects and change their own passwords. Auditor. This role grants users permissions to view all configuration data on the system, including logs and archives. Users with this role cannot create, modify, or delete any data, nor can they view SSL keys or user passwords. Guest. This role grants users permissions to view all objects on the system except for sensitive data such as logs and archives. Users with this role can change their own passwords. No access. This role prevents users from accessing the system. Local user account creation. You can create a new user in the GUI as well as TMSH. To create a user in the GUI, go to System, Users, and then click Create. When you create a local user account, you must give the account a name and password. You must also set the user role, either by retaining the default user role or by assigning a new one. The default user role for local, non-system maintenance accounts is no access. Only users who have been granted the administrator or user manager role can create user accounts. If the user role assigned to your account is administrator, you can create a user in any partition of the system. If the user role assigned to you is user manager, you can create a user in any partition to which you have access. Properties of a local Big IP system user account. User name specifies the name of the user account. The Big IP system is case sensitive, which means that names such as all uppercase Jones and capital JONES are treated as separate user accounts. There is no default value for this. Partition. When viewing the properties of an existing user account, displays the name of the partition which the user account resides. All partitionable Big IP system objects, including user account objects, have the partition property. Note that you cannot edit the value of this setting, and there's no default value. Password specifies a password that the user will use to log into the Big IP system. There's no default value. Role specifies the user role that you want to assign to the user account. Default value, no access. Partition access specifies the partition to which the user has access when logged onto the Big IP system. If you have permission to do so, you can assign this value to a new user account or change this value on an existing user account. This setting appears only when the user role for the account is not administrator. Accounts with the administrator role always have universal partition access, that is, access to all partitions. Default value is all. Terminal access specifies the level of access for the Big IP system command line interface. Possible values are disabled and advanced shell. Users with the administrator or resource administrator role assigned to their accounts can have advanced shell access, that is, permission to use all Big IP system command line utilities as well as any Linux commands. Default value is disabled. Objective 7.08. Explain how to modify user properties. There is a link here. Using the configuration utility, you can easily display a list of existing local user accounts and view the properties of an individual account. Only users who have been granted the administrator or user administrator roles can view the settings of other user accounts. If the user role assigned to your account is administrator, you can view any user account on the Big IP system in any partition. If the user role assigned to your account is user manager, you can view any user account in any partition to which you have access on the Big IP system. To summarize, depending on their own partition access, users with a user manager role can do some or all of the following: change another user's password, change another user's role, change the partition on which the other user can access objects, applies only to users who have both a user manager role and access to all partitions, enable or disable terminal access. Local user account modification. You use the configuration utility to modify the properties of any existing local user account other than the root account. When modifying user accounts, consider the following. Only users who have been granted either the administrator or user manager role can modify user accounts other than their own account. A user with the user manager role can modify only those accounts that reside in the partitions to which that user has access. For example, if user Nelson has a user manager role and has access to partition B only, he can modify only those user accounts that reside in partition B. Even in this case, however, for user accounts in partition B, user Nelson cannot modify a user's partition access property. If, however, user Nelson has a user manager role and has access to all partitions, he can modify all user accounts on the system. This includes changing another user's partition access property. Users with any role but no access can modify their own user accounts to change the password. These users cannot modify any other properties of their own user accounts. Note, when a user changes his own password, the system automatically logs the user off of the configuration utility. The system then requires the user to use the new password for subsequent logins. This behavior applies even when the new password matches the old password. Users with the role of user manager can modify all of the properties of their own user accounts except their user role and partition access. If you have an administrator role, you can also change some properties of the root account. Specifically, you can change the password of the root account, and you can enable or disable access to the Big IP system through SSH. Warning: the administrator user role provides access to the Big IP system prompt. If a user with the administrator user role is currently logged onto the system, and you change the user role to a role other than administrator or resource administrator, the user can still run commands at the Big IP system prompt until he or she logs off the system. Delete local user accounts. If the account you are using has the administrator or user manager user role, you can delete other local user accounts. A user with the administrator role can delete any user account on the Big IP system in any partition. A user with the user manager role can delete user accounts on the Big IP system in only those partitions to which she has access. When you delete a local user account, you remove it permanently from the local user account database on the Big IP system. Note, you cannot delete the admin user account, nor can you delete the user account with which you are logged in. Warning: the administrator user role provides access to the Big IP system prompt. If a user with the administrator user role is currently logged into the system and you delete the user account, the user still can run commands at the Big IP system prompt until he or she logs off the system. Remote user account management. Rather than store user accounts locally on the Big IP system, you can store them on a remote authentication server. In this case, you create all of your standard user accounts, including usernames and passwords, on that remote server using the mechanism supplied by that server's vendor. Once you have created each user account on the remote server, you can then use the Big IP system to assign authorization properties, user role, partition access, and terminal access for each account, for the purpose of controlling user access to Big IP system resources. Important: you can assign authorization properties to remotely stored user accounts on a group basis. You can then use the single configuration file, SCF, feature to propagate those properties to other Big IP devices on the network. The configuration utility stores all local and remote access control information in the Big IP system's local user account database. When a user whose account information is stored remotely logs into the Big IP system and is granted authentication, the Big IP system then checks its local database to determine the access control properties that you assign to that user. Note, the configuration utility refers to remote user accounts as external users. An external user is any user account that is stored on a remote authentication server. Important: only users with the role of administrator can manage user roles for remote user accounts. Also, if a user with a local user account is logged into the Big IP system and you subsequently switch the system from local authentication to remote authentication, the local user remains authenticated until the user's login session terminates. Remote user account server specification. One of the tasks you perform with the configuration utility is to specify the type of remote user account server that currently stores your remote user accounts. The available server types that you can specify are Active Directory or Lightweight Directory Access Protocol, LDAP, Remote Authentication Dial-In User Service, or RADIUS, Terminal Access Controller Access Control System Plus, TACACS Plus. When you specify the type of remote server, you can also configure some server settings. For example, you can specify the user role you would like the Big IP system to assign to a remote account if you do not explicitly assign one. Once you have configured the remote server, if you want any of the remote accounts to have a non-default user role, you can explicitly assign a user role to those accounts. If the remote authentication server is an Active Directory or LDAP server and is set up to authenticate SSL traffic, there is an additional feature that you can enable. You can configure the Big IP system to perform the server-side SSL handshake that the remote server would normally perform when authenticating client traffic. In this case, there are some preliminary steps you must perform to prepare for remote authentication using SSL. Section 8. Managing Existing System and Application Services. Objective 8.01. Modify and manage virtual servers. Given a proposed virtual server configuration change, outline the scope of the change and for which connections those changes will affect. Active connections, new connections, persistent connections. GUI study in the VLabs. This blueprint topic is related to choosing the correct answer for a scenario type of question. For most questions like these, obviously hands-on study is the best way to master. This topic would be an example of an existing virtual server configuration that is being modified. If you were to add a profile or an iRule to a virtual server, what would be the impact to the existing or new client connections? Build out a basic virtual server on the LTM and see what different profile changes do to client connections. Given description of an application, identify the correct virtual server configured for it. HTTP, HTTPS, TCP, UDP, VLANs, enabled, route, domain. GUI study in the VLab. Again, hands-on is recommended. With the description of an application, you can tell how a virtual server will need to be configured. For example, if you had an SSL-protected virtual server and needed to do cookie insert persistence, how would this be configured at a high level? The virtual server would have to terminate the SSL traffic with a client-side SSL profile to be able to apply the HTTP profile so that you can process the HTTP traffic to insert a cookie into the header. Given a situation where a virtual server configuration change did not appear to immediately take effect, determine why. Again, hands-on study is the best way to figure this out. This topic has to do with recognizing that changing settings on the virtual server may not immediately look as if anything changed. The scope of the change and behavior of the type of change will define who and how the changed clients will be affected. Some changes do not affect existing connections, only the new connections after the change is made will be affected. Objective 8.02. Modify and manage pools. Distinguish between disabling a member and forcing it down. And there's a link here. The Big IP system designates two terms for network devices to which a Big IP system load balances traffic. Nodes and pool members. A node is identified as the network device's IP address, such as 10.10.10.10. A pool member is identified as the network device's IP address, the service port on which the pool member is listening, and the name of the pool to which it belongs. For example, my pool 10.10.10.10.80. You can set the node and pool members to a disabled or forced offline state. When you interrupt access to a network device for maintenance, you should change the state of the node to disabled or forced offline. If the node is set to disabled or forced offline, any pool member in the Big IP configuration that uses that same IP address is also set to disabled or forced offline. Alternatively, when you disrupt only some services on a device, you should change the state of the affected pool member to disabled or forced offline. For example, if you want to change the state of the HTTP, HTTPS, and FTP pool members using the server IP 10.0.0.10, you should disable or force the 10.0.0.10 node offline. If you want to only change the state of the HTTP pool members running on address 10.0.0.10 and port 80, you should disable or force all 10.0.0.10.80 pool members offline. When set to disabled, a node or pool member continues to process persistent and active connections. It can accept new connections only if the connections belong to an existing persistence session. When set to forced offline, a node or pool member allows existing connections to time out, but no new connections are allowed. Determine use cases for disabling a member. GUI study in the VLabs. If the administrator needs to make changes, such as configuration maintenance to a server, that is the resource of a pool, but wants to gracefully allow users to finish what they are doing, then they should set the pool resource to disabled. Determine use cases for forcing down a member. If the administrator needs to take a resource out of a pool immediately due to a critical misconfiguration or system error that is impacting business, they can set the resource to forced offline. Given a situation where a pool member has been disabled but still appears to be receiving traffic, determine the cause. Setting the pool resource to disabled will allow the current users to finish their sessions but not start new connections to this resource unless the virtual server is using persistence. If the virtual server is using persistence, then the persistence record will be honored until it expires. Thus, the administrator could disable a pool member and that member can still receive new connections from the existing persisted clients. Articulate the characteristics of a pool member that has been disabled or forced offline, such as for new connections, persisted connections, etc. Setting the pool resource to disabled will allow the current users to finish their sessions but not start new connections to this resource unless the virtual server is using persistence. Setting the pool resource to forced offline will allow current connections to finish but will not allow any new connections to the even if persistence is configured on the virtual server. If the administrator needs to stop all connections immediately from a pool resource without any completion of the current connections, then removing the pool member from the pool will kill all connections immediately. This is not recommended for day-to-day maintenance, but is an option for emergencies. Conclusion. This document is intended as a study guide for the F5201 TMOS Administration exam. This study guide is not an all-inclusive document that will guarantee a passing grade on the exam. It is intended to be a living doc and will be updated as necessary. Thank you for using this study guide to prepare for the F5201 TMOS Administration exam, and good luck with your certification goals. And there are thanks from Eric Mitchell, who is a Channel FSE. And I also thank you for listening to me fumble through this document. My name is Wendy Corbin. I'm a 25-plus year veteran of IT work, and I have been working with application delivery controllers, F5 included, for about 10 years now.